Hello, everyone. It is 4:30, so it is time to start our session. I would like to tell you a few words about the organization of this session. My name is Krzysztof Turzyński, and together with Antonio Enea Romano, I will be chairing this session. And of course, the program was shown to you all before my face appears on screen. Now, I would like to add a few words about the particulars. So first, there are some breakout rooms created. So if you click on the breakout room icons, you can find 5 rooms which are named after famous physicists. So if you have a feeling that you'd rather discuss a little bit in a more private place, please use one of those breakout rooms, especially if you would like to interact with a speaker a little longer. So this is an equivalent of sneaking out of the conference auditorium and discussing in the hall. So the organizers of the conference encourage this kind of interaction. Our session is very small and cozy, so I think that it will be rather easy to organize. Nonetheless, I would like to draw your attention to the timing. So each speaker is allotted 25 minutes, and I assume that 20 minutes are for the presentation and 5 minutes are for discussion. So I will try to indicate the passage of time by showing you, if necessary, by showing you the time that is left for your talk. Are there any questions regarding the organization of the sessions, so we can settle this before we start discussing physics? I can't see any, and I would like to introduce the first speaker of the session, Keisuke Inomata, who will tell us about primordial black holes and inflation. So, Keisuke, please show your presentation, and the floor is yours, metaphorically speaking.
So, can you see my screen?
Yes.
Okay.
Your screen is visible.
Okay, thank you for the introduction. I'm Keisuke Inomata, a postdoc at the University of Chicago. In this talk, I'm going to talk about my recent work. So this one, in collaboration with Evan McDonough and Wayne Fu. This work is about the infertile potential, which can realize the large enhancement of the perturbation required for primordial black hole scenarios. Okay, so let's get started. First, let me show you the overview of this talk. So in this talk, I'd like to propose a new type of infertile potential, which can realize a large enhancement of perturbations, which is required for primordial black hole scenarios. These are infertile potentials, and so this kind of potential has been studied in many previous works. So there is a flat region in the infertile potential, and due to this flat region, so around this flat region, infertile slows down, then the perturbations are enhanced. So this kind of infertile potential has been studied in many works. On the other hand, in this work, we focus on this kind of infertile potential, which has a downward step. So there's no flat region, but still perturbation can be enhanced if this downward step is sharp enough. So this is what I'm going to talk about in this talk. Okay, so this is the overview of this talk. Okay, so let me begin with the introduction. First, let me explain what primordial black hole is. Primordial black hole is a black hole which is produced by a large density perturbations in the very early universe. Very early universe means the era where stars have not appeared yet. So very, very early universe. So this picture is a schematic picture of the PBH production. So this is the situation after the inflation era, like a radiation dominated era or matter dominated era. So at first, the perturbations are on super-horizon scales. This means that the scale of perturbations is larger than horizon scales. At some point, the scale of perturbation is comparable to horizon scale, which is called horizon entry. If the density perturbation is large enough, at this moment, the primordial black hole is produced. The mass of primordial black hole is nearly equal to mass inside the horizon. So this means that the PBH mass is determined by the time, depend on when the large density perturbation entered the horizon. In other words, PBH mass is controlled by the scale of perturbations. So this leads to the fact that PBHs can have various mass, such as 10 to the 20th gram primordial black hole can be a candidate of dark matter, and 30th gram mass primordial black hole can also be the candidate of the black holes detected by the LIGO-Virgo collaborations. So this is the motivation for primordial black holes, and recently many people have been studying primordial black holes. And in order to realize this kind of PBH scenarios, we have to consider large density perturbation. So this is a schematic picture of the power spectrum of curvature perturbation and the scale of perturbation. So as you already know, so left-hand side corresponds to the large scale and the right-hand side corresponds to small scales. As you know, on large scale, we have already measured the amplitude of power spectrum, which is about 2 times 10 to the minus 9, like this. On the other hand, so PBH scenarios required 0.01 power spectrum, like this. So in order to realize the PBH scenarios, like a PBH dark matter or LIGO-Virgo PBH, we have to consider how to enhance the power spectrum by order 10 to the 7th on small scales. So we have to consider how to enhance the perturbation. Then, so in previous work, many people studied this kind of infertile potential. This is just a review. So under the slow roll approximation, like this, power spectrum can be approximated by this. H is the Hubble parameter. Epsilon is a slow roll parameter, which is given by this, so which is proportional to the square of the inferton velocity. So this means that if the inferton slows down, the epsilon decreases. So this means that perturbation is enhanced. So the large enhancement of power spectrum can be realized by the flat region of the inferton potential, because around this region, the perturbations slows down due to the Hubble friction. Of course, this potential works, and this mechanism works. So that's why many people have been studying this kind of potential. So this is just a review. So now let me move on to main content of this talk. So as I said, in this work, I focus on this kind of inferton potential. So this potential has a downward step. So this is totally opposite to the previous models, which has a flat region, but still perturbation can be enhanced. So this is interesting. Of course, to realize the enhancement, the slow roll condition must be violated. Otherwise, so otherwise the acceleration of infraton increase the epsilon. The increase of epsilon leads to the decrease of power spectrum. So we have to violate the slow load condition. So the acceleration of infraton must be very large. This means that this step must be very sharp. But once the downward step is very sharp, the perturbations are enhanced. Okay, so let me explain why the enhancement occurs. So why the perturbations are enhanced. In our case, the epsilon changes as this. So epsilon is proportional to the square of infraton velocity. So this is a schematic picture of the infraton potential, and we denote the tau 1 as a conformal time just before the transition, and the tau 2 just after the downward step. So in this model, the epsilon instantaneously changes epsilon 2 at this downward step, and we assume that epsilon 2 is much larger than the original value. And so point is that if this transition occurs instantaneously, the curvature perturbations holds these relations. So point is that so this transition occurs instantaneously, the curvature perturbation doesn't change. So curvature perturbation remains constant. After that, the infraton roll down the other slope. So during this phase, the infraton get decelerated due to the hypofriction, like the ultra slow roll period. So epsilon adiabatically decreases to epsilon 3. So now in our model, we assume that the slope of the infraton potential is almost the same at both sides of the downward step. And during this adiabatical change of epsilon, the power spectrum of curvature perturbations increases proportionally to the inverse of the epsilon on subhorizon scales. So due to this adiabatic change, the final power spectrum is enhanced by epsilon 2 over epsilon 3. So again, point is that this instantaneous change is important. If this change is not instantaneous, curvature perturbations decreases proportionally to the epsilon minus first. Yeah. So this is why the enhancement occurs. And this enhancement can be interpreted as the particle production. Generally speaking, once the infraton experiences the non-adiabatic evolution, the particles can be produced on subhorizon scales. Here, non-adiabatic means that the time scale of the step transition is much shorter than the oscillation time scale of the perturbation, which is the 1 over k. K is the wave number of the perturbation. So let me explain what's going on in this mechanism with this equation. So during the inflation, curvature perturbation can be written like this. So this is curvature perturbation, and this is infraton fluctuation. So as I said, during the rolling down the step, curvature perturbation remains constant, and the epsilon increases. So this means that this is constant, and the epsilon increases, and this means that infraton fluctuation increases. So infraton fluctuation is enhanced. So this can be interpreted as the particle production of infraton field, like this. So so this is the physical interpretation of this mechanism. Okay, so now let me check that this kind of perturbation enhancement mechanism can really occur in concrete potential. So we consider this kind of infraton potential as a fiduciary example. This is the base potential, and this F induces the step, which is given by this. And yeah, so we consider this kind of infraton potential. This faint figure is the overall infraton potential, which is not so important. So this picture is a zoom in picture on this region. And this is a downward step. So downward step appears between phi1 and phi2. And CMB scale corresponds to here. So infraton roll down this downward step like this. So this downward step enhances the perturbation very much. Okay, so with this infraton potential, we get these results. Okay, so let me explain this. Left figure shows the power spectrum of curvature perturbation, and the right figure shows the evolution of the epsilon and eta. Okay, so let me explain left figure. Okay, so this vertical line corresponds to the inverse of a horizon scale at the transition, at the beginning of the transition. So tau 1 is the conformal time at phi equal phi1 here. So this is, yeah, roughly speaking, this is the horizon scale at the transition. And we take different value of delta n step. Delta n step is the E-fold, which is taken for infraton to pass through this downward step, pass through this region between phi1 and phi2. So for example, if we take delta n step equals 0.5, the infraton pass through this region in 0.5 E-folds. Okay, so we take these parameters, and the point is that small delta n step corresponds to sharp downward step. Of course, we fix the height of step. Okay, thank you. So of course we fix the height of a step, but we just change the width of a step. So small delta n step corresponds to sharp downward step. On the other hand, large delta n step corresponds to large, broad downward step. So from this figure, we can see that large delta n step, in other words, broad downward step doesn't enhance the perturbation very much. This result is consistent with our physical interpretation associated with particle production. So as I said, the particle production is related to the non-adiabatic evolution of infraton. So if the downward step is broad, the infraton doesn't experience the non-adiabatic evolution. So the particle production doesn't occur efficiently. So that's why the perturbations doesn't grow even if we fix the height of step. Okay, so apart from that, so we can see that from this figure. Okay, so let's look at the solid line. So from this figure, we can see that, so this is a solid line shows the epsilon. So from this figure, we can see that epsilon has never been smaller than the original value. So horizontal axis E-folds and the time goes from left to right. So epsilon has never been smaller than the original value. So even in this case, the perturbations can be enhanced. And in addition to that, the damping of small scale side is determined by the cutoff of the particle production. So, okay, let me explain that. As I said, in order to produce the particle with no adiabatic evolution of the infraton, so we have to satisfy this condition. If we consider very small scale, this means that if we consider large K, this right-hand side becomes small. So at some point, this inequality is not satisfied anymore. So this means that if we consider very small scale, particle production doesn't occur. So this means that enhancement doesn't occur. So that's why at some point, the enhancement doesn't occur. So this sharp cutoff of the enhancement is related to the particle production interpretation. Okay, so finally, let me mention some unique difference from the previous works. So the order of perturbation enhancement is determined by the length of flat region in previous works, because in previous works, in previous models, the amplitude of the perturbation enhancement is determined by how much the infraton velocity decreases around this region. So in the flat region. So if we consider long flat region, then infraton get decelerated very much. So yeah, which leads to the large enhancement of perturbation. On the other hand, in our model, the amplitude of the enhancement is determined by the height of downward step. So this is the total difference. And the other another difference from previous work can be seen from this small scale side of the peak. So as I said, this small scale side of peak is determined by the cutoff of the particle production. On the other hand, in previous works, this small scale side of peak is controlled by the infraton potential slope, which follows the flat region. So yeah, so this is determined by this region. And apart from that, there is an oscillatory feature in the power spectrum, which is associated with the particle production, but there is no oscillatory feature in the previous models. So we might be able to use this kind of a unique feature to discriminate our mechanism from the previous mechanism. Okay, so let me summarize my talk. So in this talk, I have proposed a new type of infraton potential which can realize a large enhancement of perturbations required for previous scenarios. So this is the previous models, and yeah, this is the new type of model which I have focused on in this talk. And this enhancement is related to the particle production associated with the no adiabatic evolution of the infraton field. Okay, so I stop here. Thank you.
Thank you very much. So, Anna?
Yes. So thank you, Keisuke, for a very interesting talk. If anybody has some questions, please ask now.
So we are a small party, so we don't have to raise our hands, so we can just start asking questions. Meanwhile, I'll allow myself asking a question. And this models with flattening of the potential usually require a lot of fine-tuning. So how would you comment on fine-tuning in your scenario?
Okay, fine-tuning, yeah, of course, we have to fine-tune the potential. So one is that the height of potential. So yeah, as I said, the perturbation enhancement is determined by the height of potential. And the other fine-tuning, okay, is required for, give me a second. Okay, yeah, so we have to fine-tuning of this region. So I mean, infraton So we have to tune the length of the how should I say? So okay, so once the infraton roll down the potential, then the infraton get accelerated. So, but at some point, the so infraton decelerated by the hyperfriction. So this downward step position is important for the pH mass scales. So we have to tune the position of downward step. So yeah, there are two fine tunings of the position of downward step and the height of downward step. So if we perform the two fine tunings, then yeah, we can realize the pH scenarios.
Okay. Can I ask you also another question if nobody has another?
Yes. Yes.
So you were mentioning that you need to violate slow roll condition, correct? So
Yes.
I assume that this is because what would be normally a decay mode it becomes a growing mode. Is this the reason why there is this perturbation enhancement? Because normally this is how this is can be understood in terms of the study of the solution of the equation of the curvature perturbations.
Mm-hmm.
I don't know if because I haven't checked your paper, but you solved numerically the equation for curvature perturbation, correct?
Yes.
So you solved.
Okay.
Yes.
Yeah.
Sorry. Okay. Go ahead.
Yeah. I just numerically solved the Mukhanov-Sasek equation.
Yeah. Correct.
Mm.
So there is a way to write down one of the two solutions, which is the one which on super horizon scales would be for a slow roll model would be a decay mode, but I think that in your models, in this class of models, it becomes a growing mode because epsilon is decreasing very fast, something like that. It's similar to ultra slow roll if you want. It's like it's a temporary ultra slow roll phase if you want.
Yeah, of course, our mechanism is related to the ultra slow roll period. Actually, there is an ultra slow roll period which follows the downward step because the infraton gets accelerated. The infraton has a very large kinetic energy. So in that case, the universe becomes like a ultra slow roll period. So as you said, yeah, this mechanism is related to the ultra slow roll period. Yeah, exactly.
Okay, but the shape of the potential that you're considering produce different features with respect to the cases which were studied in the past. Okay.
Yes, yes.
I would just say that these oscillations that you see are kind of normal, actually. I mean, if you most of the time you always have this oscillation, but probably you know, this has to be checked model by model. But I wouldn't say it's so peculiar.
Okay. Okay. Thank you for your comment. Yeah.
Thank you.
Okay, I think that we need to move on to the next speaker. And
thank you very much.
Thank you.
Thank you very much, Keisuke. Our next speaker is Albert Escriva, and he'll be talking about numerical simulations. And we can't escape black holes for now. So, of course, this will be about the primordial black holes. Albert, please.
Yes, so let me share the screen. So I think now you see, let me go here. You see, no, the screen?
Perfect, yes.
Okay,
yes.
Thank you. So yes, I am Albert Escrivá. I am in University of Barcelona. I defended my PhD thesis actually 2 weeks ago, and I will move 1st of September for the postdoc. So I am going to talk about numerical simulation of primordial black holes, specifically into specific topics. Basically, what I'm going to explain is based on this. The first paper, well, I'm going to explain the basics how to simulate numerically the formation of primordial black holes. And the second one is precisely what I want to explain that we did, Antonio, Enea Romano, and myself, about the size and the effect of shapes of the curvature peaks for pH formation, okay? Before that, let me explain more or less the motivation of the PVH scenario. No? So we already know, but it's always good to remember. So we know that in the universe there is something that we don't know what is its composition, which is the dark matter. No? And there are different scenarios, different theories, approaches, but one of the most promising is primordial black holes, no? Because you don't need basically to introduce new physics and so on. So this is, for instance, the last constraint plot that you can find in the literature of Card and Kuhnel. So, well, as you can see, there are some windows available where you can find that PVH can constitute a large fraction of the dark matter. No? Of course, these constraints are updated currently, and in the next few years, the updates are going to increase. And of course, we will have more outputs of the Virgo-LIGO collaborations. No? So it's promising times to work on the PVH scenario. So basically, the point is that during inflation, you can have very rare peaks sufficiently large that could have undergone through gravitational collapse during the radiation epoch, and these peaks could have formed primordial black holes in the very early universe. Okay. And the point is that in a radiation epoch, you can assume that these rare fluctuations, since come from inflation, have a spherical symmetry. And therefore, you can assume that when you have these cosmological perturbations in the universe, no, they collapse, undergo through gravitational collapse, following a spherical symmetry. Okay. So basically, the sketch, simplified sketch is this. You have the universe filled by a perfect fluid in a Freeman-Robinson-Walker background. And then, of course, what characterizes if a perturbation is going to collapse or not is a parameter that is called the threshold, okay? The threshold of PVH formation. And delta is what is called the, well, you can call it the amplitude of the perturbation. No? So, of course, if the amplitude of the perturbation is higher than the threshold, then this perturbation, the gravitational collapse is stronger in comparison with pressure gradients, and then, of course, collapses and form a black hole. Otherwise, if the amplitude is lower than the threshold, then the pressure gradient disperses the perturbation and the black hole is not formed. Okay. So basically, these kind of things are important because statistically, the probability to have a large fluctuation is exponentially small. Okay, and as was shown in a recent paper a few years ago, the abundance of PVH are exponentially sensitive to the threshold. Okay, so the threshold can be, well, there was some analytical estimations time ago, no, these two basically. But as was shown, actually, this threshold for PVH formation is profile dependent. And you can see that these estimations only depend on the fluid, of the kind of type of fluid, no? So are not accurate, no? So as was done here in this other paper, we made an analytical estimation to find the threshold for PVH formation. You can find more details there. I'm not going to explain, but it's important to mention for next things. So of course, another thing is that when you have a collapse of these density perturbations on the Freeman background, what happens is that first is formed an apparent horizon, and then follows a process of accretion of energy density from the Freeman-Robinson-Walker background that increases the mass of the PVH from the time of formation of the apparent horizon until a stationary state, let's say, okay? So the point is that there was some properties of the PVH form at the time of horizon formation that were not explored numerically in terms of the different profiles of curvatures that you can have. Also, for instance, the constant, well, the PVH mass follows a critical scaling law, and the constant in front of this scaling law, I will comment more details later, was not explored in the literature substantially. And also the effect of the accretion of the Freeman-Robinson-Walker background to the PVH mass. Okay, this has never been explored, and is precisely what we wanted to solve. No? So what I'm going to do now is explain more or less quickly how you can simulate numerically the process of collapse of these density perturbations. No? So what you need, first of all, is the differential equations, which in this case are Misne-Sharp equations, which describe the motion of a relativistic fluid under a curved space-time. And to get these equations, you just need to consider a perfect fluid with this expression. Also, you assume a spherically symmetric space-time. And then, well, you can define some invariant quantities that helps to simplify the equations. If you solve then Einstein equations with these inputs, you get all these parameters well, all these equations, sorry. Then the capital M, for instance, is the inertial mass, capital R is the Aurelian radius, okay? Rho is the energy density, U is the Aurelian, the radial velocity, sorry. Then this is the definition of the inertial mass, which takes into account the kinetic and potential energy. Also, you have here the Hamiltonian constraint that you monitorize for numerical convergence, and also the lapse function, okay, which is given by capital A. And this is a generalized Lorentz factor, is an auxiliary equation. No? So you have all these differential equations, and the next thing is that you need to characterize the cosmological perturbations. No, so as was shown by Shibata and Sasaki time ago, the previous metric that I showed you can be, well, is equal at superposition scales at first order in gradient expansion is equal to this metric, which is a Freeman-Robinson-Walker metric with a curvature, with a radial dependent curvature, okay? And then with this curvature, you characterize a cosmological perturbation, the density contrast. And then the point is that the criteria for PVH formation is done using something called compaction function, which is basically the mass excess of the perturbation under a given volume, under a given sphere or radius capital, well, Aurelian radius, no? So, well, you can, solving the Misne-Sharp equations, gradient expansion, using the gradient expansion method, you can build the initial perturbations, these given by these tilde variables in terms of the curvature K. Okay, you can do it. There are much more details in the paper, and then you should apply some boundary conditions. Okay, which are these ones to solve numerically this problem. Okay, so the condition for PVH formation basically follows using the compaction function, as was shown time ago. So you consider the peak of the compaction function measured at Rm, where Rm is the location of the peak of the compaction function, and you say that this peak is precisely the value of the critical compaction function is precisely, gives you precisely the value of the threshold. Okay, so if the peak is higher than the threshold, you have PVH formation. If the peak of the compaction function is lower than the threshold, then you don't have formation of black holes. Okay. So also this numerical code time ago was solved using an hydrodynamic code using finite differences. What I did, for instance, is well, solve it with spectral methods. Okay, so you consider Runge-Kutta for time derivative, no, and then spectral methods for spatial derivative. About this method, there are much more details in the paper. Okay, so I skip. Just I tell you. So for instance, consider that you have a Gaussian profile, no, this one, an exponential. So in this case, the threshold of PVH formation is given by this value with this accuracy, okay? And then, well, following the gradient expansion method, you can find that this, as I told you, this density contrast is related with this in terms of the curvature profile, okay? So for instance, this is a simulation that you have an initial compaction function, you see, Gaussian, and then you evolve numerically, no? So what you see is the compaction function. You have taken an initial peak higher than the threshold. And then, of course, the compaction function increases. Here, at roughly 1, you will form an apparent horizon. And as I told you, this simulation will continue with an accretion process, okay? Process of accretion from the Freeman-Robinson-Walker background. Instead, in the case when you take the peak of the compaction function lower than the threshold, oops, no, this is not the case. Yeah, so critical, sorry. So in this case, if the peak is lower than the threshold, then as you can see, it decreases the compaction function and the fluid is dispersed on the Freeman-Robinson-Walker background, okay? So yes. So of course, as I told you, consider the situation that the perturbation collapses, no? An apparent horizon is formed. Then, as I say, no, the PVH mass increases by the accretion of the Freeman-Robinson-Walker background. Let me tell you that in this point, with the numerical code, a singularity is formed because, well, of course, you form an apparent horizon and then the coordinates are singular. You continue evolving in time. There are more details in the paper. And what you have to do is perform an excision technique. So basically, you remove from your computational domain the part where you have the singularity, okay? And then you continue the simulation without the singularity, and then that's it, no? So basically, what we wanted here, as I told you, is look what happens with the physics in this process, no? From the time when the apparent horizon is formed, until the time that the PBH is already, let's say, stationary. No, the final mass of the black hole doesn't change. No, so in all this process, as I told you, we wanted to check different things, and what we have considered is two families of curvature profiles parameterized by a parameter Q. This parameter Q basically tells you how is the shape around the compaction function, okay? Because I don't explain, but the threshold of PBH formation, as we did in other paper, the threshold can be parameterized in terms of Q, okay? Is this analytical equation that I told you that appears in one of the papers that I did. So basically, well, the important thing is that we parameterize the curvatures with these two families of profiles, and then they look like this, okay? For instance, you have the red line is basically a polynomial profile, so using these bases, okay, of profiles, and then you have the exponential. So the red line is the basis with parameter Q equal 1. The green line, for instance, is, well, the exponential with also Q equal 1. Blue is with Q equal 1, but with lambda equal 1 as well, which means that here you see the density contrast. The peak of the overdensity is not centrally peaked, no? So the peak is not centered at 0, and so on, okay? And you have two limiting cases. This dotted line here is when you take Q going to 0, and then the other case, limiting case, is when you take Q going to infinite, okay? This sharp profile. So basically what we wanted to check first of all is the properties of this magnitude. So this is the ratio of the time of apparent horizon formation, so the time that takes the black hole to form the apparent horizon in terms of the time of horizon crossing, when the time when the length scale of perturbation crosses the horizon, the cosmological horizon, then also the mass of the black hole when the apparent horizon is formed in terms of the mass of the horizon, and then the radial radius of the black hole in terms of the Hubble horizon, okay? So basically, what you have here is the time of the apparent horizon formation in terms of the amplitude of the perturbation, delta. Well, here the notation is a bit different, but it's the same, is delta, no? And for different profiles, no? So as you can see, it's obvious when you have a large perturbation, no? Then of course the time that needs to form an apparent horizon, then of course it's reduced. When you increase delta, then the time formation is much lower, as you can see, no? The tendency is clear. Another thing is what happens with the final mass, sorry, with the mass of the black hole at the time of horizon formation. In this case, again, when you increase delta, the mass increases, obvious, no? It has, this perturbation has more amplitude, more energy density, and therefore the mass is increased. And then another thing, which is actually maybe the most interesting, is the radial radius, okay? In this case, the same behavior is clear, no? You have large perturbations, large delta. If you increase, then the increase of the size is clear, no? But we wanted to compare precisely these values with an analytical approximation that was done time ago by Arada and Carr in this paper. And they say that, well, this ratio, the max value of this ratio follows this equation in terms of omega, and for a radiation fluid is basically 0.31, okay? And precisely we wanted to see what happens contrasting this approximation with our numerical values, okay? So basically, this is what we have got, and of course, we can get this following, well, taking into account these numerical results, no? But this is just the summarized result. So here, in terms of Q, you can find numerically each maximum value of this ratio, and then the red line is the analytical estimate. So as you can see, there is a region in terms of Q where this analytical approximation is a bit violated, but it only happens for, okay, thank you. But it only happens for very large perturbations, okay? For small perturbations, it's perfect. This analytical approximation works very nice. You can see here, no? The bond, this analytical bond is basically at 0.3. So you can see that all these values are within this approximation. Only when you have very large perturbations, okay, you can see that there is a region where this approximation is violated, okay? So well, this is something that we did. Another thing is what happens with the final mass of the black hole. The final mass of the black hole after the accretion process from the Freeman-Robinson-Walker background follows this law, this scaling law. This comes, well, this was tested time ago. This gamma is a universal value, okay, given by this value. This delta C depends on the profile. And then this constant K depends on the specific profile that you are considering. No? So in the literature, there was not an exhaustive range of values of this constant K. Okay, so we wanted precisely to check what range of values it takes, the constant K, no? Because maybe it could be substantially large and maybe it could be possible to form very large black holes, no? And actually, this is what we have got. In terms of Q, as I told you, Q is the way that we use to parameterize the different profiles. The value, the constant K goes from like 3.5 more or less. Of course, you can see that it depends on the profile, more or less. But you can see it increases a lot. Okay, it could be substantially large. Here, we have not been able to numerically solve the problem because when you take Q going to 0, these profiles, as I've shown you in a plot, are very sharp, the density contrast, and therefore it's a bit problematic to simulate them numerically. But as you can see, it could be substantially large. In the literature, there was some range of values like order between 1 and 10, a Fudicial range of values that are not too much accurate. But as you can see, it could be substantially more large, like 2 times, no? And the minimum is 3.5. And the last thing that we wanted to check is precisely the effect of the accretion of the black holes, no? So the ratio between the final mass of the black hole in terms of the mass at the horizon. Well, here is F and I, okay, it's inverted, but it's the same, no? So of course, what we expect is that it will depend on the shape of the profile, of course, and also it will depend on the amplitude of the perturbation. And actually, one of the main motivations to do this is precisely on this work of Helling-Deng, John Regan, and Alexander Vilenkin. I think that Helling-Deng is doing a talk also. In this work, they found, if I am not wrong, that the maximum factor of the accretion for the collapse, PH formation from the collapse of the main walls was a factor 2. So precisely, we wanted to check if this factor 2 also appears, well, also we have in the case of the collapse of density perturbations, no? It was something interesting to see, no? What happens in a different scenario of PH formation. So this is what we got. For instance, so this is, well, the amplitude minus the critical amplitude of the perturbation in terms of Q, okay? And you have here for different Qs, for different profiles, okay? The different circles, triangles, and stars corresponds to different families of profiles, the ones that I shown you, okay? So you can see that the accretion of the PVH follows like more or less a V-shaped parabola, okay? But you can see that there is a maximum always. We expected that the maximum will have appeared for the maximum value of the amplitude of the perturbation, which is given by this, well, here. The maximum value of the perturbation is 2/3, okay, using the formalism that we follow. And we expected a maximum value of the, okay, thank you, a maximum value of the accretion at this value, okay, at 2/3. But actually, no, you can see that there is a maximum, okay. Of course, this is related with the compensation of the gravitational collapse of threshold gradients. If you take a higher perturbation, then the black hole collapse earlier, then you have accreted already much more mass than at the time of formation of the parent horizon. In comparison, if you wait a lot of time until you get the maximum value of the black hole mass, okay, so there is a known of nonlinear processes. And it's interesting to point out that when you form black holes with mass roughly the mass of the horizon, which are precisely those PVHs more statistically significant for the abundances, then you can see that the accretion effect is roughly 3 times. Okay, this is a value that we found that was never explored in the literature. So to summarize and to finish, basically, well, we have checked analytical approximations of the PVH mass, time, and radius at the time of the horizon formation. Okay, and we have verified these analytical approximations. Also, we have studied the accretion effect of the PVH from the Fromenson-Walker background, and we have seen that it could be substantially large for large PVH. It could be like a factor 8. For a small PVH, as is already known in the literature, is remarkably small. And finally, it will be interesting maybe to reproduce results in the case of non-spherical symmetry to see how it depends in terms of the non-sphericity, the accretion from the background. So yes, thank you very much.
Thank you very much.
Hi, can I ask you a question?
Please.
Hi, so one quantity that I'm particularly interested in is the black hole formation time. So I used to think that the black hole is formed soon after the perturbation re-enters the horizon. So roughly speaking, the black hole formation time is the horizon time. But later I learned that black hole could be formed much later than this. So have you extracted any information regarding the black hole formation time? Thank you.
So for instance, this ratio here is precisely the time of that takes the black hole to form the parent horizon in terms precisely of the time of horizon crossing. So as you can see, when the perturbation is large, yes, the parent horizon is formed, let's say, very soon after the time of horizon crossing. But when you have small perturbations, let's say, it takes much more time. And then the accretion process also takes much more time. So if the black hole is very large, the time of horizon, the time this AH is formed is very small in comparison with the time of horizon crossing. And then the time that takes the black hole to accrete the mass from the background is, yes, is very small in comparison with the small black holes.
I see. Thank you.
Any more questions?
Let me ask a question. When you calculate the accretion from the Friedman-Robertson-Walker background, how accurate are those results? I mean, like when you start with a given potential and a given inflationary trajectory, inflationary history, and then you start the formation of PBHs, how accurately could you, for example, estimate the dark matter content in the PBHs?
Estimate the dark matter abundances, you mean, from these?
No, or generally, I mean, the effect of the accretion process.
Well, for the accretion process, what we are doing is, you make, as I say, the accretion technique. Numerically, you have to do this process. And then what you do is, of course, this process takes, let's say, an infinite time. No? So in principle, you will have to leave the computer making the simulation, I don't know, 2 months or so until get an, I don't know, a stationary value when the increase of the mass of the black hole is lower than, I don't know, 10 to the minus 5%. No? Of course, we are not doing this because it will take time. So what we are doing is, let's say, make an interpolation of the mass of the black hole in time using a formula, but I don't remember the name. I don't remember the name now. It was Russian researchers. But yes, you interpolate the formula, and with this you can estimate the final mass of the black hole. So the deviation is like 2% more or less.
Okay, thank you.
Okay. Do we have time for one more question, Christoph? Or
yes, we do.
Okay. So I wanted to ask you very briefly, this factor of 2 and 3 that you were mentioning in the end, do you think it is important for estimations, of black hole abundance, or this factor of 2 is used or not when people do estimate abundance?
This factor 2. No, I think not, because when you estimate the abundances, you are taking into account, let's say, the final mass of the black hole already. You don't, let's say, the mass of the black hole at the moment of formation of the parent horizon doesn't enter in the abundances. So yes, this factor 2 is.
But when people do approximation, they necessarily have to to, I mean, if you do an analytical approximation, you have to consider the mass at the time of horizon crossing, because that's the point up to which you can trust perturbation theory. So I was asking this thing because when people do this kind of analytical estimation, I assume that they are considering the mass at that horizon crossing time and then somehow extrapolate from that the final mass. I don't know how, but that's what I was asking is.
Yes. What people does generally is, take that the final mass of the black holes, all the black holes that they consider is roughly the mass of the horizon. But yes, of course, it depends on the scaling law. It depends on the profile and the constant K also. So, so yes.
Okay.
Thank you very much, Albert. Thank you very much for the presentation and for the discussion. And now we should move on to the next speaker of the session. So again, we'll be hearing about primordial black holes, but this time in the context of modified gravity. And the speaker is Sergio Vallejo Peña. Sergio, the floor is metaphorically yours.
Okay, thank you, Christoph. Good day to everyone. Can you hear me?
Yes, very well.
Okay, thank you. Now can you see the screen?
Yes.
Now it's perfect.
Okay, thank you. So as Christoph said, I'm going to talk about what are the effects of the modification of gravity on the production of primordial black holes. This talk is based on this paper that I wrote with Professor Antonio Romano. And this is going to be a very general talk. I'm not going to talk about any specific like case where PBH are produced, but about the general mechanism of the enhancement of primordial curvature perturbations in a modified gravity theory. So as an introduction, I want to mention that from the Planck results, there is room for deviation from a power law spectrum, as you can see in this figure that I took from the Planck collaboration. And you can ask what are the sources of these features? What is the source of these features? And these features are also important, as we have been discussing here, because these features can produce primordial black holes, which could be in the observable range of LIGO and probably in the future in the observable range of LISA. And they can also be part, or they could be all of the present dark matter in the universe. So these are very important objects to study. So these features in the primordial power spectrum leading to PBH formation or to the deviation of the invariant scale invariant power spectrum can be, for example, in single field models, minimally coupled to gravity with standard kinetic term, which I will call X inflation for brevity, can be due to temporary violation of the slow roll conditions, as we have discussed, as have been discussed in previous talks. They could also be due to multi-fields, for example, multiple fields, multiple scalar fields, also vector and tensor fields, but the scalar parts of these fields. And it could be also due to the modification of gravity, which is the case I'm going to discuss here. And in particular, I want to discuss the case of G-inflation, which is a particular case of Ordenski's theory. So I will show you what is exactly this theory. So G-inflation is basically a theory where there is a scalar field, which I will call phi, which is minimally coupled to gravity. And this field is coupled to gravity according to this action that you can see here, where this X is basically the kinetic term. R is the Ricci scalar, and K and G are some arbitrary functions, and we will use some this system of units in which the speed of light and the Planck constant are equal to 1. So in this theory, you can compute the energy momentum tensor, the stress energy momentum tensor, which is in general given by this expression, where these quantities are just this derivative respect to the kinetic term of the Lagrangian of the field, which is basically this part of the action, and this other, which is like an effective pressure of these theories. And this is very important, the energy momentum tensor, because we need to define the curvature perturbations in the moving gauge, which is a gauge defined by a condition which is imposed on the energy momentum tensor, specifically on the 0I component of the energy momentum tensor. And this is actually very important, and this is a very important part of our work. So we consider general scalar perturbations around the flat Friedmann-Lemaitre-Robertson-Walker spacetime. So the most general metric around this spacetime, this background, can be written in this form in an arbitrary gauge. And we decompose the scalar field and the stress energy momentum into the background and perturbation pairs using this notation. Basically for the scalar for you that under a gauge transformation, these different perturbation quantities behave according to these relations. So they transform according to the relation under this gauge transformation. And here the prime denotes derivatives respect to conformal time. So we need the perturbed stress energy momentum tensor for this theory. We can compute the background components of the stress energy momentum tensor, which are given by these relations here. And one important thing we need is the 0I component of the perturbed energy momentum tensor at linear order. So this is basically the expression for the energy moment for this component of the energy momentum tensor in this theory. And this is a very important relation that we will use in our computations later. So usually when people study curvature perturbations in these theories and in single field theories, the unitary slices gauge is a very common use gauge to define these quantities. And in single field models with the standard kinetic term and even in K-inflation, as I will show later, the unitary gauge and the moving gauge are the same. They basically coincide. So when you study curvature perturbations in this gauge, in those kind of theories, you are studying the curvature perturbations in the moving gauge, which are directly related to CMB observations and also to the process of PVH formation. But in general, in our density theories, and for example, in these G-inflation theories, the unitary gauge and the moving gauge do not coincide. And this is very important. This has to be taken into account if you want to compute correctly the power spectrum of moving curvature perturbations and all the observables that depends on this quantity. So the unitary gauge is defined by this condition. Basically, the perturbations of the field vanish. So this condition gives us the necessary time, the necessary conformal time translation to go to the unitary gauge from any arbitrary gauge, which is basically given by this relation here. So we can compute the curvature perturbation in the unitary gauge, which we will call zeta, and basically is this quantity here. And we can also define other gauge invariant quantities. For example, we can define the unitary gauge lapse function, which will be important as you will see later in the talk. So basically, the action and the equation of motion for the curvature perturbation in the unitary gauge is already known in the most general case of Ordenski's theories, and in particular, G-inflation is just a particular case. So this is the action for G-inflation as well. And these functions, GS and curly FS are just functions of K and G and their derivatives, and can be computed, for example, for the case of G-inflation or well, in this case for G-inflation. From this action, you can get the equation of motion for the unitary curvature perturbation, and you can write this equation in for the Fourier transform of the curvature perturbation. Basically, this would be the equation for the Fourier modes of the unitary curvature perturbation. And this equation will be used, we will use it later to know when the spectrum of moving curvature perturbation can be enhanced in order to get PVH in these theories. Now, I want to define the moving slices gauge, which is defined by the condition that these components of the energy momentum tensor vanish. So we know that from the expression that I showed earlier for this component in G inflation of the energy momentum tensor, it transforms according to this condition, to this relation here. So it allows us to get the time translation necessary to go to the moving slices gauge from an arbitrary gauge. So this is the general time translation. And in the case in which G does not depend explicitly on the kinetic term, which is this case, the conformal time translation necessary to go to the moving gauge coincides with the conformal time translation necessary to go to the unitary gauge, which shows that in these cases, the moving gauge coincides with the unitary gauge. And this is something we expected, because in this case, this theory reduces to a K-inflation theory, and it is already known that in K-inflation, the unitary gauge coincides with the moving gauge. And basically, the curvature perturbation in the unitary gauge is the same as the moving curvature perturbation and can be used for to compute all the observable effects of this primordial perturbation. So we can define the moving curvature perturbation using this conformal time translation. And something we can ask now is, what is the relation between the moving curvature perturbation and the unitary curvature perturbation? So to obtain this relation, we can simply use the conformal time translation required to go to the moving gauge from the unitary gauge. So from this expression here, evaluated in the unitary gauge where delta phi is equal to 0 and A is just the lapse function in the unitary gauge, we can just obtain this conformal time translation, and the relation between the moving curvature perturbation and the unitary curvature perturbation will have this form. But we would have this gauge invariant quantity here, this lapse function in the unitary gauge. So we want to get rid of this term or express it in terms of the curvature perturbation in the unitary gauge. And we can do this easily just by using these Einstein's equations, these components of the Einstein's equations in the unitary gauge. So basically this perturbed Einstein equation in this case is this equation you can see here. So we can, from this equation, obtain a relation between the lapse function in the unitary gauge and the curvature perturbation in the unitary gauge, and replace it in this expression to finally obtain a relation which only involves the curvature perturbation in the moving gauge and the curvature perturbation in the unitary gauge. And we can write it in this simple form, expressing all these things as a function which we call the enhancement factor, because in the case in which this function is very large and this derivative of the curvature perturbation in the unitary gauge is not 0, this could cause large difference between the moving curvature perturbation and the unitary curvature perturbation, and this could be a mechanism to produce an enhancement of the moving curvature perturbation. for example. So now we can compute the relation between the power spectrum of theta and R. Basically, we can get this relation between the two power spectrums. There is a term here which shows the difference between the two. And basically, when the curvature perturbation in the unitary gauge is constant, this term in the relation between the curvature and the unitary, the comoving and the unitary curvature perturbations is zero, this term here. Basically, the two quantities coincide, and the curvature perturbation in the comoving gauge is also a constant, so the two power spectrums are the same, and delta is zero. This can also be considered to be true in the case in which this is approximately constant, so theta prime is approximately zero, and this will be important in the next slide. So there is something I want to remark here. The opposite is not true. If the moving curvature perturbation is constant, then the unitary, this doesn't imply that the unitary curvature perturbation is constant. So this is something which is important to take into account. But the superhorizon growth of perturbations cannot last forever or indefinitely, because if this happens, the perturbation theory breaks down, and we want it to work. We want to produce physical and observable results. So because of this, it is expected that at some time before the end of inflation, the unitary curvature perturbation will coincide with the moving curvature perturbation. And this will be important, thank you, for producing the enhancement of the power spectrum. So this simplifies the calculation of the moving curvature perturbation. And this is important because the evolution of moving curvature perturbation can be traced during and after reheating, but the evolution of the unitary curvature perturbation is not understood in these epochs. So it is easier to consider the moving curvature perturbation. So how can we get an enhancement of curvature perturbations in these theories? So basically, we go back to the equation describing the evolution of theta, which can be written in this form. And from this equation, we can find superhorizon scale solution, which has this form. And we can obtain from here the general condition for superhorizon growth in a similar way that is obtained for single fields with standard kinetic term. Which is basically this condition here. During inflation, this term is positive. So basically the condition reduces to this condition, the time derivative of this quantity f has to be greater than zero. So in G inflation, this condition reduces to this relation here, where this is with this epsilon here is the slow roll parameter defined according to this relation. So this is the relation or the condition necessary to produce an enhancement of curvature perturbations in G inflation. This condition for the case of X inflation reduces to the already known condition for the enhancement, which is the temporary violation of slow roll. Basically, we have that in this case, the theory of G inflation reduces or has this specific form for G and K. So this function called GS reduces to the Max Planck square times epsilon. So the condition reduces to this condition here. And since this term is always positive, this reduces to this, which is already known. This is the condition that has been explored in the literature for the past decades to enhance the curvature perturbations in single field models, like I call X inflation. So in G inflation, the superhorizon growth can be achieved if this gamma and delta have opposite signs, contrary to X inflation, where the sign of delta is fixed. And it's also important to mention that this superhorizon growth can be achieved during a slow roll, but in X inflation, superhorizon growth can only be achieved if there is a temporary violation of slow roll. Okay, so now I want to relate this to the production of PVH formation, basically this enhancement, and I want to review very briefly the production of primordial black holes. These things I'm going to discuss are just estimations. So the mass of the PVH can be approximated according to this relation, where this MH is the horizon mass at horizon crossing time. But as I said, this is just an estimation. More accurate treatment would involve a scaling relation, as discussed in the previous talk. From this relation, you can compute the present time a fraction of PVH against the total dark matter, where this beta is the energy density fraction of PVH at formation time. And beta can be written in terms of the probability of the density contrast. If the density perturbation follow a Gaussian distribution, then this beta can be approximated according to this expression here, which ultimately depends on the power spectrum of co-moving curvature perturbations. And this is why the co-moving curvature perturbation is very important for PVH production. So more accurate calculation would involve the use of the results of numerical simulations, and the choice of the window function could affect the results of the calculation. So these things should be taken into account. And these estimations of the PVH abundance can be also affected by the shape of the power spectrum, non-Gaussianity, nonlinear statistics. So all these effects should be taken into account if you want to make numerical computations of primordial black holes in these theories. So what is the effect of the modification of gravity on PVH abundance? So basically what happens is that at the end of the anomalous superhorizon growth of theta, it will coincide with R, and as a consequence, the power spectrum of the moving curvature perturbation would be enhanced. And this is the important aspect regarding the PVH production in this in this scenario. This enhancement of the power spectrum would increase the deviation of the standard deviation of the density field, the sigma function, and as a consequence, the energy density fraction of PVH beta is affected, and you can get an increased PVH abundance. So this is a very general description of how you could get primordial black holes in these theories. We did not consider a specific model or a specific case to produce PVH abundance, but this could be done in the future. And it is also important to note that the effects of the modification of gravity on the process of gravitational collapse are not well understood now, and this would require further investigations, and this is actually a very interesting topic that one could investigate in the future. So finally, to end this talk, I want to make some conclusions. We have computed the effective stress energy momentum tensor for the inflation theories, and in particular, we have shown you the form of this component of the perturbed energy momentum tensor, which is crucial to compute the moving curvature perturbation. We have used this to derive the general relation between the unitary gauge curvature and the moving curvature perturbation. When the unitary gauge curvature theta is not constant in time, it differs from R. This happens, for example, when there is an anomalous superhorizon growth of theta on superhorizon scales, but the growth cannot last indefinitely, so they will coincide at some time before the end of inflation. And for this reason, you can use the equation of theta to compute the power spectrum of R, because eventually the two quantities will coincide, assuming that the theta will become constant at some point. And we have derived the general condition for superhorizon growth of theta, showing that slow roll violation is not necessary, and this superhorizon growth of theta will be the cause of the enhancement of the moving curvature perturbation. And we discuss how this enhancement of the spectrum of R can affect PVH abundance. In the future, it will be interesting to extend this investigation to other modified gravity theory and to use observations to constrain the different types of theories. And it would also be important to perform numerical simulations of the PVH formation process, taking into account the effects of the modification of gravity on the process of black hole formation. Thank you very much for your time.
Thank you very much. So I decided that it was important for Sergio to convey his point until the end of the talk. So we are left with time for possibly one very short question. Anyone? Okay,
maybe.
Yes.
No.
Very short.
Yes, I have a question, but it's like a general question also for one of the other conveners. If Albert knows about attempts to study PBH formation in modified gravity theories, which is the final comment which Sergio was making. But I don't know if Albert is listening to us.
Yes, no, I don't know. No, I have not heard nothing in terms of numerical simulations to see what happens in modified gravity. No, no, but it's very interesting. Yes, yes.
Mm-hmm. Okay.
Okay, thank you very much, Sergio. And we move on to the next speaker of the session. The next speaker is Heling Deng, and he will tell us about possible distribution of black holes, which is implied by LIGO Virgo. So now the screen is yours.
Thank you. Thank you. Hi, everyone. My name is Heling Deng, and I'm a postdoc at Arizona State University. Today, I would like to share with you something I did earlier this year. It's a topic about primordial black holes and the LIGO results. So due to the time limit, I will skip many technical details and mainly focus on the physics. So here's the outline. So first, I will talk a little bit about the LIGO results, and then we consider the possibility that these LIGO black holes are actually primordial black holes. And then we will consider a simple model that is able to fit these LIGO data. And lastly, I will talk about a possible mechanism that can generate these black holes. So we know that over the past few years, the LIGO-Virgo collaboration detected about 50 events. And most of them are believed to be gravitational waves emitted from spiraling and merging black holes. So here, these purple dots are black holes people discovered before LIGO, and their masses range from about 5 solar masses to 20 solar masses. And during the first run of LIGO 01, people found several black holes within the mass range about 20 to 40 solar masses, which is larger than people expected for black holes. Then during 02, people found even more black holes within this mass range. And during the first half of 03, the third run of LIGO, people found even more black holes within 20 to 40 solar masses. So here I plot the mass distribution of LIGO black holes. So in total, we have 44 confident events. So we have 88 black holes here. Here, the x-axis is the black hole mass, and in the unit of solar mass. And the y-axis, we can ignore this expression here and simply think of it as the black hole number. We see that more than 30% of the LIGO black holes are within this mass range between 30 to 40 solar masses. So we have a peak here, and the number density decreases to both ends. So this is an intriguing feature of the LIGO black holes, because we see that LIGO can also detect black holes around 10 to 20 solar masses, like these purple dots here, but they found a peak here at about 30 solar masses. The origin of these black holes is so far unknown. The possibility that they are simply ordinary astrophysical black holes from stellar collapse is under active investigation. But here in this work, we assume that these LIGO black holes are primordial black holes. So primordial black holes are black holes formed in the early universe before any large-scale structures like galaxies, usually during the radiation era. And depending on the mechanism, they can have a large range of mass. They can be as small as the Planck mass and as large as a value much larger than the solar mass, like these supermassive black holes here, about 10 to the 6 to 10 to the 10 solar masses. So the current motivation of the study of PBHs are the following. So first, people think they could be the seed of supermassive black holes because it's hard to explain the existence of these black holes at the center of most galaxies by the standard accretion model of astrophysical black holes. And then people also consider the possibility that they are LIGO black holes, which is the main topic of this work. And also it's been a long been studied that PBHs could be a candidate of dark matter. So here are some observational constraints of PBHs as dark matter. The x-axis is the black hole mass, and the y-axis is the fraction of dark matter in PBHs. So if the fraction is 1 here, it means that all dark matter can be explained by PBHs. So we still have this window where PBHs can account for dark matter. But in this talk, I will be focused on this region, 10 to the 34 solar masses, which is the mass range of the LIGO black holes. So the picture of the formation of PBH binary is actually quite simple. So in the early universe, these primordial black holes can be thought of distributing randomly in space. And they are living in the homogeneous radiation background. Due to cosmic expansion, they do not interact with each other in general. However, it's possible that with some small probability, two black holes are formed very close to each other. In this case, the gravitational attraction between these two black holes could defeat the cosmic dilution, cosmic expansion. Then they would form a binary. If there's no disturbance from the environment, for example, these black holes or perturbation in the radiation fluid, they would simply collide head to head. However, due to, for example, a nearby third black hole, for example, here, this black hole could exert different gravitational forces on these two black holes. So normally they would form a binary and they were in a spiral. And at late times, these black holes just go away and we have a binary. If the coalescence time of the binary is comparable to the age of the universe, because LIGO detected these black holes at a very low redshift, which is practically the current epoch. So if the coalescing time of the binary is comparable to the age of the universe, then they could be detected by LIGO. Now let's consider how many of these binaries can be detected by LIGO. To do that, we first need this important quantity, which is the PBH mass function. So it's defined by m times dn divided by rho CDM. Here, dn is the number density of black holes within the mass range m to m plus dn. So m times dn is the energy density of the PBH. And when we divide it by rho CDM, which is the energy density of dark matter, we have the fraction of dark matter in PBHs within this small mass range. And then if we take the integral, we will have the total fraction of dark matter in all PBHs. Here in this talk, I will focus on this definition of mass function, F, which is the multiplication of the mass of the black hole times this psi here. The physical interpretation of this mass function is that it is the fraction of dark matter in PBHs with a mass around m. So this is the mass function we will use in this work. And from this mass function of the PBH, we can find the probability that they could be detected by LIGO. Here I will skip many details and simply focus on the physics here. From this mass function, we can find the merger rate, intrinsic merger rate of a certain event. So a certain merging event is characterized by three numbers, M1, M2, and Z. Here, M1, M2 are the black hole masses in the binary system, and Z is the redshift when this merger takes place. And this intrinsic merger rate, R, should be proportional to Fm1 times F of M2. Now, not all these merger events can be detected by LIGO. We can only detect mergers that can reach the Earth today. And this number should be proportional to the merger rate. Now, even if these mergers can reach the Earth today, it doesn't mean they could be detected. So we have this detection probability. So for example, first of all, the merger frequency should be at the detection range of LIGO. And also, this detection probability also depends on for example, the position of the binary in sky or the orientation of the binary system. So we have these detection probability as a function of these three numbers. Now, from these two quantities, we can get the probability of each event. So if we specify three numbers, M1, M2, and Z, we can find from these two the probability of an event Pi of M1, M2, and Z. And we can also find the expected number of detection NE of a certain time range. For example, LIGO detected 44 confident events during, I don't know, maybe 300 days. And from this mass function, we can predict this NE that can be detected by LIGO. So from these two, if we combine all these events, we can eventually get to the likelihood of all LIGO events. Here I ranges from 1 to NO, where NO is just 44. It's the number of events detected by LIGO. So we have 44 probabilities, P1 to P44. And we also have this P Poisson because these LIGO signals they follow a Poisson process, and it should satisfy this distribution here, where NE is just this NE, the expected number of detection, and NO is 44. This NE, which can be predicted by our model of the mass function, should not deviate much from 44. If it's much smaller than 44, then this is 0. If this is much larger than 44, then this also goes to 0. So what we do in the following is that we would like to maximize this likelihood and constrain our mass function. Now, before doing that, we need a model of FM. Now, when I looked at this distribution, mass distribution of LIGO black holes, the simplest model I can think of is a broken power law. So it has a peak at M star, and on the two sides, we have two different slopes. So this mass function is assumed to follow this broken power law. When M is smaller than M star, it's M to the alpha 1. It's when M is larger than M star, it's M to alpha 2. So now we have this very simple mass function, and it is only characterized by 4 numbers: FPBH, alpha 1, alpha 2, and M star. So now what we like to do is to put these 4 numbers into here, the mass function, and we go through this process and calculate this likelihood. And we would like to maximize this likelihood, and then we can use the number to constrain these 4 parameters. And here are the results. So we found that when FPBH is approximately 10 to the minus 3, and alpha 1 is 1.2, alpha 2 is minus 4, and M star is 35 solar masses, we have the maximized L. For example, here when alpha 1 is 1.2 and M star is 35 solar masses, the darkest spot is here, so it corresponds to alpha 2 being equal to minus 4. All right, so this is the final result. So by fitting the LIGO data, we found that if we assume that the mass function follow this broken power law, then we can actually explain these LIGO events quite well, as we can see in the next slide. So the mass function follows this relation. So it's m to minus to 1.3 when m is smaller than 35 solar masses, and when it's larger than that, the slope is -4. And the FPBH, the fraction of dark matter in these PBHs is 10 to the -3, which is about 0.1%. So now we have this mass function, right? And then we can use this mass function to calculate this probability of each event. So given M1, M2, and Z, we can calculate the probability, which means that we can draw random samples from this probability distribution. So LIGO only ran for about 300 days, but we can use computer to extract as many samples as we want. So we can mimic the detection of LIGO for maybe thousands of years. So assuming that Fm satisfies this relation, we draw about 50,000 samples from the probability distribution, and we found this. So here, this blue histogram as before is what LIGO detected, and this orange curve is our result. So we drew 50,000 samples, and we found this smooth curves. And we see that this curve actually agrees with the LIGO results quite well. As a comparison, I also plotted this green curve, and this is from the so-called log normal distribution of PBH. This is the most popular distribution mass function in the literature because it's the mass function derived from PBH from inflation. But here we see that the best fit log normal function does not agree. Thank you. Does not agree with LIGO results very well. Now we have this mass function. The question we want to ask is there any mechanism that can generate this power law, this broken power law mass function? The answer is yes. So actually, a motivation of this work is that in a previous study of PBH mechanism, we found a mechanism that can generate this broken power law, but this is different from the popular scenario. So in the popular scenario, these PBHs are from density perturbations from inflation, but here our mechanism is a non-perturbative quantum effect, which is quantum tunneling, or sometimes referred to as first-order phase transition. So in order to generate these black holes, we need to have an extra scalar field. So here we have two fields, phi1 and phi2. And this phi1 can be think of as the inflaton field. So during the slow roll, if there's another vacuum near the slow roll, and this vacuum is separated with the inflationary vacuum by a barrier, then quantum tunneling can happen. So during inflation, we can have some random formation of vacuum bubbles. And after inflation ends, the inflaton rolls down, and these bubbles would immerse in this radiation background. After these bubbles are formed, due to the pressure difference, they would expand very rapidly, almost at the speed of light. So after inflation, we will have some bubbles that expand with a huge Lorentz factor, and they run into the ambient fluid. And this bubble is characterized by three numbers. Rho B which is the vacuum energy inside the bubble, and rho I, which is the radiation density outside the bubble after inflation, and also the sigma, which is the surface tension of the bubble wall. And then by solving the Israel's junction conditions, we can find the equation of motion of these bubbles. And then, depending on the bubble size, we have two scenarios of black hole formation. The first one is called subcritical. In this case, the bubble simply, the bubble radius increases, then it stops with respect to the Hubble flow, and then it will shrink, and then it will collapse into an ordinary black hole. The other scenario is more interesting. So if the bubble grows after inflation to a size that's larger than the de Sitter horizon associated with the interior vacuum energy, then this bubble would inflate. When an inflating region is surrounded by an non-inflating region, we would have a wormhole. And this bubble simply grows into a baby universe, which is connected to our universe here in the pink region by a wormhole. After this wormhole throat pinches off, we would have a black hole for either an outside observer and an inside observer. And we are interested here, so we can see a black hole here. By doing some calculations and simulations, we found that the black hole mass in these two scenarios actually follow different relations as a function of the bubble radius. And a roughly example here is that when it's subcritical, the mass is proportional to r cubed. When it's supercritical, it's proportional to r squared. And these are the origin of the broken power law behavior in the mass function. So due to the time limit, I will just skip this. And I would like to say our mass distribution is determined by 5 parameters. Lambda, which is the bubble nucleation rate during inflation, and gamma I, which is the Lorentz factor, how fast the bubble grows after inflation, and also these 3 parameters associated to the bubble. Now we fix these 4 parameters, lambda, sigma, rho I, and rho B, and we only increase the Lorentz factor. And we found a mass function like this. So if we increase gamma I, we see that the mass function grows like this. It evolves like this. And when gamma I is very large, we see that the mass function here at the supercritical region actually is proportional to n to -4. This is exactly what we want from the LIGO results, right? We want the slope to be -4. And the question is, can we find a slope that is approximately 1.2 at the subcritical region? And the answer is yes. And this is the black curve that we found. And this is the observational constraints on PBHs, and we are interested in this region within the range of LIGO black holes. And if we plot this black curve in this region, we found the following. So this is actually our final results. So the black curve is the mass function from our mechanism. And these 2 straight orange lines are the broken power laws. And this is m to the 1.2, and this is m to the -4. And as a comparison, I also plotted this green curve, which is the log normal distribution. We actually see that the black curve agrees with the orange one very well. A concern about this is that we have this observational constraint here, the light blue region, which seems to violate this, they hit this orange curve, so our mechanism could possibly be ruled out. However, due to the time limit, I wouldn't get into the details, but we argue that this blue region can actually be relaxed, so our mass function is still safe. So here are the conclusions. So by doing the maximization of the likelihood, we found that the best fit parameters using our broken power law mass function, the best fit parameters give this curve, this orange curve, and it agrees with the LIGO results quite well. And we also have this blue, this black or the orange curves. So this is kind of the prediction of our model. If future LIGO results found that the curve is very different from the orange one, or the mass function is very different from this one. For example, if later observations found that the slope here is actually much larger than -4, then our model can be ruled out. So that's it. Thank you very much.
Thank you. I think that we have time for a short question, I guess.
Okay, I will ask one. Thank you for your talk, very interesting. I wanted to ask you this thing, when you compute this probability, how do you take into account what is the probability of having two black holes at a given distance? Because that's, I think, something you need, yeah, to determine the probability of the formation of a binary system.
Yes. So this is actually within this merger rate. So
Correct.
yes.
But here I see a product, but I mean, there is a more involved expression which takes into account
Yes.
also the distance. Okay,
Yes.
okay. So this is
Right.
just very schematic representation.
Yes, I'm sorry, I missed many details here. It's a long.
No, I
expression
understand.
here.
I understand.
Yes, yes.
Okay, so now I'm going to abuse my privileges to ask one more question. And how attached are you to this value 1.2 for the slope? Because of course, when you do the parameter estimation, I mean, you get this number with some uncertainty. So you can massage your tunneling model to get something that's not exactly 1.2, right? So I'm just wondering. On this plot, I'm just wondering what's the error band here?
The error band between the orange and the blue curve?
No, no. I mean, like the error band resulting from the accuracy with which you determine the slope.
Oh, you mean the error bar in 1.2?
Yeah.
Well, I didn't exactly calculate this because so one thing, so I actually neglect many details in doing this work. For example, the spin and the accretion, because these are supposed to be very rough results. We can actually have more sophisticated techniques. Some groups are doing this and they found different results. But here I would simply like to see the physics here instead of focus on the exact value. So I'm just proposing that it is possible to use a broken power law to fit the LIGO data.
Okay, thank you very much.
Thank you.
And now we should all thank Herling for his talk. And we move on to the next speaker, who is Camilo Santa. And we're going to hear about some involved numerics regarding black holes. Camilo?
Okay, so first, let me thank Christoph and Antonio for organizing this parallel session. Let me share my screen. So I guess you're seeing it now.
Yes.
Okay, so my name is Camilo Santa. I'm a PhD student in the University of Antioquia in Colombia, Medellin, Colombia. And this talks deep learning merger mass estimation from gravitational wave signals in the frequency domain. This is a study I did with Juan Pablo Marulanda, who's an undergrad student, and Antonio Roman, who's our current parallel session organizer also. So it's based on this paper. I underline here.
Camilo, I think that we are seeing your Slack page.
Oh God, let me just Slack.
I can only see your face, actually.
Really? Let me just see if maybe.
Oh no, this is we are seeing. I'm sorry, we are seeing Herling's screen. So Herling, could you unshare the screen, please? Thank you. Now everything is okay.
Yeah, but okay.
Okay, so can you see my screen, everyone?
Yes, now it's fine. Thank you.
Okay, so well, it's based on this paper. This talk is based on this paper. And the idea of this study was to do a neural network to estimate the gravitational wave masses, the black hole masses from gravitational wave signals. So it's sort of what Helen was talking about earlier. So yeah, this is like the outline of the talk. So first, I'm gonna do a brief, very small introduction on gravitational waves and how LIGO detects these gravitational waves using matched filtering. Then I'm going to talk a little bit about how we can use machine learning to do the same process a little bit faster, and how we need to generate some training data to train these machine learning models. I'm going to show some network architectures because, well, even if we say we're doing the frequency domain, we're also training a time domain network just to compare both. And I'm going to show the results of our study. Okay, so first, let's talk about gravitational wave sources. So we know from the quadrupole formula that the amplitude follows like this formula, the amplitude of a gravitational wave. So here we can note two important contributions. We see that it scales linearly with the distance. So this would help us like further on when we want to modify like the amplitude a little of our simulated waveform. And we can also see that it depends on the second derivative of the quadrupole moment. So from here, we know that there could be like 4 possible sources of gravitational waves. So one is continuous gravitational waves, which are very heavy objects like neutron star, but that have a non-zero quadrupole moment. So they might have a like small mountain, or well, they're not completely symmetric. Another source is compact binary coalescence. So it's when we have a binary system that's orbiting each other, and then they're going to merge. So this is the one we are mostly interested in. But we also have stochastic gravitational waves, which could come from the Big Bang and sort of like background noise, or burst gravitational waves. So this one could be produced by supernova. And this is very hard to simulate. So we're going to focus mostly on the compact binary coalescence. And we need very massive objects. So we're going to analyze black hole mergers. But yeah, as Helen was saying before, there's been a lot of detections between, for example, black holes and neutron stars, or neutron stars and neutron stars. This last one is very important because it also has an electromagnetic counterpart. But yeah, we're going to focus at the moment on 2 black holes, which are going to first in spiral. They start orbiting each other. And as they're emitting gravitational waves, they're losing energy. So they're going to get closer to each other, and then they're going to merge. And this produces this type of gravitational waves. So another detail is that black holes being so massive, this ring down, this in spiral and merger is going to be very short. You can see it's less than a second. So while if we are studying neutron stars, this could last for 10 to more seconds. So yeah, it's going to be short time signals. And what LIGO detects is a strain. So let's talk about the strain first. So LIGO is a set of 2 detectors. Currently, we have one in Hanford, the other one in Louisiana. And they have 4 kilometer, well, it's a Fabry-Perot interferometer, which has 4 kilometer size. Yeah, here we have like a mid station at 2 kilometers. So it's basically that. It's an interferometer which has Fabry-Perot cavities, and light bounces back and forth in these cavities like 280 times. And then they mix and they create an interference pattern. And that's how we're going to measure the difference in the leg size. So yeah, we're going to measure if one leg size changes, we can detect that by the interference pattern. Okay, so what I said, we have 2 detectors. LIGO has 2 detectors, one in Hanford, one in Louisiana. There's another one, Virgo, in Italy, and I think last year, one in Japan, and the Kamioka mine started operating last year. Okay, so these detectors have certain sensitivity. So we can see it here in this graph at the right. So this is what signals we can detect. And it can detect signals up to 10 to the, well, -22 or -21 in strain. That's around 10 to the -19 meters. So it can detect very small variations in the leg size, the leg length. Okay, and after detecting like this small variations, what it does is a process called matched filtering or matched filter, in which it's going to look for certain signals. So I have like a template bank of signals, and this is the signal I'm trying to find. And I'll do it by cross correlation. So I'm going to start sliding this signal across my detector event. So I'll start sliding it. For example, if this is our detected signals, we can see here in the red one, we can see clearly we have that same signal. In the green one, we also have, But when the signal to noise ratio is very low, it's very hard to see that actual signal. So we use this process of cross correlation. And we see that, the signal indeed appears. So when we have the signal, we have this small peak telling us that it matched the signal we were using. So for this, we would need a template bank. So we need a lot of signals we were expecting to detect. And each time I have an event, I need to compare with all of that signals in the template bank. So this could be very, very time consuming. We're going to need a lot of templates just to cover all of the parameter space. And it's going to be a very computationally expensive. So this has its drawbacks, but it works very well when the signal to noise ratio is very low. So this match filtering is going to work when we have low signal to noise ratio. What we're going to see of machine learning is very good when we have a higher signal to noise ratio. So it could be a little bit complementary. So we're going to use machine learning. Well, it's like the current trend. So we have artificial intelligence, we have machine learning, and we're going to learn from data. And inside machine learning, we have deep learning, in which we're going to use deep neural networks to learn from the data. So that's what we're going to use in this study. So the difference with traditional programming or this matched filtering is that before we had a set of rules. For example, the matched filtering, we need to do this cross correlation, and we have some data. And if we use these rules on this data, I get the answers. So I was using these rules to compute the signal to noise ratio, and the best fit would be my mass. Here in machine learning, we're going to change this a little. We have a lot of data. So we're going to generate data synthetically. So we can generate a lot. And as we are generating data with simulations, I already know the black hole masses. So I already know the correct answer. So I just pass all of this to my machine learning algorithm, and it's going to learn the rules to produce new answers. So this is like the different paradigm. Okay, so we still need this template bank. We're going to still need the gravitational wave simulations. So I'm going to have a template bank. It's around 4,000 gravitational wave simulations. And what we're going to have is that the strain signal from the simulation would be our data, like our independent variable. And our answers would be the masses, the black hole masses that produced that strain signal. And the rules are going to be the neural network. Okay, so I'm going to explain a little bit about this neural network. And for the neural network, we would have like a process of training, which consists of showing it all of this strain signals and black hole masses. And that's very computationally expensive. And we're going to need the template bank during the training process. However, this is only like, we only have to do it once. So we only have to train the neural network once. Whereas in the match filtering, we needed the template bank always for each event. Here we only need it in the training process. And when we want to do inference, it's going to be very fast. So that's the advantage of the neural network. It's going to have a very fast inference. Okay, so for this fast inference, we need, in the training process, we need to fit several parameters, several weights. So here at the right, what we are seeing is a convolutional layer where we have an image, and I'm just applying the same cross-correlation process. I'm just in 2D, I'm moving this filter across the image, I'm sliding it, and I'm producing an output map. So this is called the convolutional layer. We'll have a lot of filters, and these filters are the ones that the training process is gonna get. Besides, we're also gonna have some pooling layers. So these pooling layers, just, for example, we'll grab the max value in this sliding window or the average value. This will help us to have some invariance for time translation. So yeah, we're losing some information here, but we'll have some time translation invariance. And finally, we're gonna have some dense layers. So these dense layers will have all possible connections between different pixels or neurons. And in the training process, we need to get these weights, which are represented by the straight lines here in the image. And at the end, we're going to have an output layer, which is going to give us the masses of the black holes. So this is the process. But to train this data, we're going to need a lot of training data. So we are using some simulations called spin effective one-body numerical relativity simulations. It's like the fourth optimized version. So this does one-body simulations in the ADM formalism, and then matches some coefficients to numerical relativity. And it's like an approximation which has two different masses. So we have the black hole masses, and this is going to produce this train signal. So here we're seeing that our template band is consisted of masses from 5 to 75 solar masses, and we are avoiding like the very high mass ratios. So we have a mass ratio less than 10. So that's why we have this small missing information here. And we're going to split our database into a modeling set, which we're going to use to train the neural network, and a validation set, which we're going to use to test the neural network. Apart from generating the train signal, we need to add some noise, to make it a little bit more physical. So we're going to use LIGO's PSD, power spectral density, the one I showed before, to generate the noise. So it's going to be, according to different frequency, we're generating the noise. So here's what we generate. So we have two masses. We generate the strain signal for a given detector. And after adding noise, this is the same strain signal. We see it's a little bit hidden, but we can still, we are going to still be able to detect it. So that's the first part, generating the strain signal, adding the noise. But we're also computing spectrogram using a short-term Fourier transform. So this short-term Fourier transform divides my strain signal in small windows and then computes a Fourier transform. And this is, okay, thanks. And this is how the same signal would be in the frequency domain. So first we have like a strain versus time. Now we have a 2D image versus time. And this is my gravitational wave merger. This is how it looks when we add noise. Okay, you can still see it, sort of. And this is the training data we're going to use, and we're going to measure the mean absolute percentage error between the masses, and also the overfit. So the overfit, we're defining it as the training error minus the test error, over test error. So it's like the relative difference between the error we got while we were training and the error at the end with the test set, with validation set. So this will tell us how good it can generalize the results. Okay, so we have two different architectures. Here's a time domain network architecture. So in the time domain, we're using one-dimensional convolutions and one-dimensional pooling. And at the end, I'm left with two different masses. But we also have a frequency domain architecture. So in the frequency domain, we have 2D convolutional layers, 2D pooling layer. But at the end, I also finished with 2 merger masses, which is what I'm trying to predict. Okay, so let's see the results. So the time domain network has around 500,000 parameters, while the frequency domain network has 50,000 parameters because we have this pre-processing step. So our image is like a little smaller. And also the 2D pooling layer will reduce the image even more than the 1D pooling layer. So the frequency domain has way less parameters. So this has a regularizing effect, which will help the overfit, reduce the overfit. Okay, so we trained the network with different polarizations of the gravitational waves. So with a polarization of 0, we can see that the frequency domain has a slightly less error than the time domain. So we can see in the x-axis, we have the signal to noise ratio. As we have a stronger signal, so the signal to noise ratio increases, our error will decrease. It decreases around 5%. And we see that the frequency domain, well, has a smaller error, slightly smaller error. However, the overfit is way smaller. So this is the overfit in the time domain is way higher than the overfit in the frequency domain, according to for different signal to noise ratios. So this is a great advantage of the frequency domain network. And we repeated the same procedure with a different polarization, and we achieved the same results. So the mean absolute percentage error is around the same, but the overfit of the frequency domain is lower. It's way lower. And finally, we plotted this mean absolute percentage error as a function of both masses. And we see here at the left is the frequency convolutional neural network. And at the right, we have the time domain convolutional neural network. So the mean absolute percentage error on average is lower, it's way lower here in the frequency domain than in the time domain. So we're getting better results if we do that pre-processing step. And this is assuming a constant signal to noise ratio of 10. So yeah, it exhibits a better behavior here in the frequency domain. Okay, so let me just finish with some conclusions. So we trained a neural network to determine the merger masses, both in the frequency and in the time domain. We found out that there were less parameters in the frequency domain than in the time domain because we have a smaller image after doing the spectrogram, and because the pooling layer reduces my image even more if it's 2D than if it's 1D. And this less amount of overfit error because it's sort of regularizing the network because it's a simpler network. And as it's a simpler network, the inference is going to be faster in the frequency domain than in the time domain. We have to do less computation because we have less parameters. And yeah, in general, it works a little bit better. But well, the ideal is to have both networks working in tandem to better have a better discrimination at signals. Okay, so we have some future work planned. One of them is include more merger parameters. So here we only have the 2 masses, but we could include also the eccentricity of the orbit or the spin of each black hole. So that's one idea to analyze further. And the other one is to use real LIGO data to see if we can get the same result as matched filtering. Okay, thanks a lot.
Thank you very much. So now we can have a short discussion, and I see, so Anna, take over from me.
Okay, so thank you, Camilo. Does anybody have any question for Camilo? This talk is slightly, I mean, it's about gravitational wave detection, but you know, the specific mechanism of production of the black holes, which could have merged to produce these gravitational waves, was not addressed directly. But so let me ask you this question regarding other parameters. Like in this paper, you were considering the mass, but what about estimating other parameters of the merger?
Okay, so yeah, at the moment, we could also estimate different parameters. So what we would have to do is just here in the training data, we would have to generate all the parameter space. So we would have to get different eccentricity, different spins for all of the black holes, and we would generate the strain signal for each combination of parameters. And at the end, we would just need to change this network architecture, changing the amount of parameters here at the last layer, the amount of parameters we want to detect. Yeah, but it's completely possible. Thanks.
Okay, thank you very much. We exhausted the time that we could allocate to questions, and thank you so much for the presentation and for this short discussion. And we move on to the next speaker of the session. The next speaker is Javier Olmedo, and he will tell us about the predictions for the CMB in inflationary and anisotropic cosmologies. So please, the floor is yours.
Thank you. Thanks a lot. I would like to thank the organizers for letting me give this presentation here. I had to apologize because I'm not going to say anything about black holes, but I will discuss some anomalies in the CMB that one can get when you break the isotropy principle in your cosmological model. So this is some work I have done in collaboration with Ivana Guyot and Srinath Vijayakumar. There are like some few papers where you can find all the details about our collaboration. So as you know, most of the models that we consider for the early universe, they are models that are homogeneous and isotropic. Namely, they are described by a single scale factor that is usually expanding. Planck observations also support this principle, or at least they did not confirm a departure from it. However, at the largest scales in the CMB, Planck is not able to constrain considerably the data. So there is still some room for speculation and for discussion about the presence of some anomalies at those large scales. For instance, dipolar anomaly, quadrupolar anomaly, and so on and so forth. And our perspective is that perhaps these anomalies are coming from new pre-inflationary or inflationary physics. So here we decided to study what happens when you break the isotropy of the space-time. Namely, you allow a spatial metric that has 3 different scale factors that they can evolve independently. And this happening before inflation. So this is something that was already studied in the 2007 and 8 by Pereira, Pitro, and Osan. They consider a standard quadratic inflaton potential coupled to a Bianchi-1 spacetime with 3 different scale factors. They introduced cosmological perturbations on these scenarios, and they discussed that this an early anisotropic evolution breaks scale invariance of the power spectrum. It also breaks isotropy, inducing higher multiples in the CMB, and also induce scalar tensor and tensor cross correlations, because this anisotropic evolution induces some shear of the space-time that couples dynamically the 3 types of perturbations that you have in these cosmological models: scalar perturbations and tensor perturbations with the 2 polarizations. However, they found an obstruction when studying these scenarios in classical general relativity. And the reason is that when you go to the high curvature region before inflation, you can find, due to the probably some of you know it, the BKL conjecture. Some of the scale factors, they can actually bounce and start expanding rather than contracting and going to zero, to the singularity. And this makes or gives problems for the to have a well-posed initial value problem for perturbations. Therefore, I think this is one of the reasons why I decided not to continue studying these models. But actually, there is another possibility that one can consider. Let me assume that we have a bouncing inflationary model, namely a cosmological model where you don't reach the singularity, but actually you have a bounce that can happen at Planckian scales or not, but the scale factor never goes to zero, and then you enter in a universe that was contracting in the past. So in this kind of scenarios, that are the one I'm going to consider here, anisotropies dilute very fast from this bounce, and therefore you recover an FRW model. You can give initial data to perturbations, do evolution through the bounce where anisotropies are going to be large, and then enter in the inflationary expansion and see how the initial state of perturbations at the onset of inflation look like. And the answer, I will anticipate it, is that it's going to be very, very different from the one of the Bunch-Davis state, at least for large scales. For ultraviolet scales, they don't see very much anisotropy, so you recover the standard model, the standard prediction, but at large scales, you will see strong departures from isotropy and scale invariance. So what we did is that we just complete or provided a Fock quantization for perturbations, where anisotropies are not treated perturbatively. We had to rely on numerical tools, of course, but we don't need to do any perturbative expansion for the anisotropies. We also provide the power spectra in a very precise way at the end of inflation, and we actually can use constraints in the quadrupolar anomaly reported by Planck collaboration in order to actually find upper bounds to the maximum amount of anisotropies in our spacetime around the bounds. And we also, given that we satisfy these constraints, we compute new observables, the TB and EB angular correlation functions that are zero in the FRW limit in the standard model. So let me briefly explain what are the kind of bouncing scenarios that we adopt here. We consider loop quantum cosmology and isotropic scenarios. Loop quantum cosmology, maybe you never heard about this, but it's a simplified, let's say, version of loop quantum gravity that is a quantum gravity candidate that tries to make compatible general relativity with quantum mechanics. In loop quantum cosmology, what people do is just apply loop quantum gravity techniques to cosmological models, and then you get some modified cosmological model that you can see in an effective way as a standard GR with an exotic fluid that is coming from quantum correction from LQC that is important, is large at high curvatures and is Planck order, but otherwise this stress tensor dilutes very rapidly and you enter in classical general relativity very fast. This tensor violates energy conditions, and this is the reason why you never reach the singularity, but actually you get a bounce. So in these models, it was shown that the energy density of the inflaton, the mean Hubble parameter, and also the shear scalar that accounts for the amount of anisotropies of the spacetime, they all are bounded above. They have universal upper bounds. So in this model, we have well-defined equations of motion. We give initial conditions at the bounds when defined by when the mean Hubble parameter vanishes. And here we fix the amount of anisotropies, how they are distributed with this psi function. And we also fix the value of the inflaton at the bounds. That essentially is telling us the amount of e-folds of expansion that we have during inflation. Together with a judicious choice of the scale factors, we get something like you see here. Here I am showing you the kinetic energy of the inflaton, the value of the potential. Here is a quadratic potential. We fix the max using Planck data. And we also show here the amount of anisotropies, the shear scalar squared, properly normalized. As you see here, around the bounds that happens at t equals 0, energy density given by the kinetic contribution is maximum, and then it decreases to the past and to the future. Similarly, this happens to the shear scalar. Actually, the shear scalar dilutes very fast when you enter the slow roll regime. So you enter here in an FRW regime very, very fast, the standard model. And in the past, you still have anisotropies that go to 0, for instance, at 10 to the 3 Planck seconds before the bounds. And for the modes of perturbations that we see in the CMB, these anisotropies are irrelevant. Namely, if you start evolution here or before this time, the results that you obtain do not depend on this choice of initial time. So what about perturbations? Perturbations, they satisfy some second order differential equation like the one you see in equation 1. And it has, or there are anisotropic properties that are going to be kept by perturbations. One is due to the Laplacian that involves the 3 different scale factors. This is the physical wave number in the Fourier space. And you also have, in addition, time-dependent potentials that couple all type of perturbations, and that depends on a given k, a given direction in the Fourier space. Of course, the coupling is for modes that point in the same wave number. Modes pointing in different directions, they are decoupled. Here, gamma 0 represents the scalar mode or the Mujano-Sasaki variable, or it is related, you also want, to the comoving scalar perturbation. Gamma 1 and gamma 2 represent the 2 tensor perturbations for the linear that are linearly polarized, plus and cross. However, in our discussion, it is more convenient to define or to consider tensor perturbations in the basis in which they show circular polarization. That is called the helicity basis. In this basis, you can expand the Fourier modes as linear combinations of elements of an orthonormal basis of complex solutions to the equations of motion that I will denote here by V of lambda and S. Lambda represents the 3 different orthonormal solutions. S represents the entries of scalar or tensor type that these solutions will have. They are normalized with respect to the inner product that you see here. This inner product is preserved upon evolution in equation 3. And you see that it involves all type of perturbations, scalar-like and tensor-like perturbations. In order to quantize these perturbations, you just need to expand the Fourier modes in these as combinations of these basis elements. The coefficients in the linear combination represent the annihilation and creation variables that satisfy suitable commutation relations, and they actually define a particular vacuum state by the usual condition that probably you have seen many, many times. And let me just remind you that the choice of these bases is equivalent to the choice of vacuum state and vice versa. And the basis that we choose is such that we are in the standard Minkowski vacuum, or for people that are more familiar with 0 order adiabatic states, 10 to the 3 Planck seconds before the bounds. If you start the evolution at this time or before, the results that you obtain that do not depend on that choice of time. With this, you can compute the power spectrum, just taking the expectation value of 2-point functions. This power spectra can be written in terms of the elements, combinations of the elements of the basis of solutions, and they satisfy several properties. In particular, they depend on a couple of spin indexes, S and S prime. If S and S prime are equal, power spectra are real and positive. Otherwise, they are complex. And they satisfy, in addition, 3 other conditions that are due to the reality conditions that the modes have to satisfy, commutation relations of these Fourier modes, of the perturbations. And finally, we are choosing a vacuum state that is parity invariant, because the background metric is also parity invariant. This is another property that the power spectra will have. You can do evolution using numerical tools. compute the power spectra at the end of inflation, and there it is convenient to expand the power spectra as linear combination of spin-weighted spherical harmonics in a multiple expansion. These multiples, remember that since the spin-weighted spherical harmonics are 0 if the multiple L is smaller or equal than the absolute value of the spin label S, this implies, for instance, that the only multiples that are going to survive in the isotropic limit in the standard FRW model correspond to the monopolar multiples L equals 0, and for them, the only power spectra that will contribute are those that are diagonal, when S and S prime are equal. And in this way, you recover the standard scalar power spectrum and the two tensor power spectrum that are actually equal. So here, let me show you the monopolar contribution in this anisotropic evolution solution or background that we have considered. The power spectra, as you see in the horizontal axis, the Fourier mode, this is the comoving wave number K, is normalized, okay, thank you, with respect to the pivot scale provided by Planck, that is 0.05 megaparsec to the -1. If you go to smaller scales, you recover the standard model. If you go to large scales comparable to the horizon, you get some enhancement of power in the scalar power spectrum. You can actually see that there are additional multipolar contributions. Here I show you the quadrupolar contributions compared to the monopolar one of the scalar power spectrum. Here, monopolar contribution dominates against the other ones. And still, they can contribute, and you can use these quadrupolar contributions in order to constrain the parameter space. Here, what we saw is that you can fix, if you fix the amount of anisotropies, there is a minimum value for the inflaton at the bounds that has to give you the sufficiently large number of e-folds in order to get this quadrupolar anomaly to be in a sufficiently restricted region in such a way that you can satisfy the constraints. Given these anomalies, we can compute the angular correlation functions. Let me just very briefly say that the tensor power spectrum shows a stronger coupling to the anisotropies, and this is why you see here that quadrupolar anomalies in the tensor power spectrum are stronger. Similarly, you will have tensor cross correlations and scalar tensor cross correlations that are some of the multiples are non-negligible. And the most interesting part perhaps is here when you compute the angular correlation functions using the standard transfer functions that you can obtain by evolving the usual Boltzmann equations during recombination. Here, let me just mention that due to the properties of the power spectra and the parity properties of the transfer functions, there are components of the even and odd angular correlation functions that are going to be identically 0, but there are others that are not. Diagonal are not diagonal components. Now let me show you here very fast the calculations that we have obtained. Here I compute also the TT angular correlation function for the largest scales in the CMB compared to the off-diagonal components of this angular correlation function when L prime is equal to L plus 2, for instance, and M and M prime are equal 0. Here you see that at the largest angular scales, these off-diagonal elements are comparable, or a fraction that is considerably large with respect to the diagonal elements. These off-diagonal components, they die very rapidly as you go to higher multiples, smaller angular scales. But still, this guy here, the blue line, is within the cosmic variance of the standard model. This is not happening when you look at the BB angular correlation functions. In the largest scales, we get a stronger enhancement in such a way that the prediction in our model makes to be outside the cosmic variance. Again, if you look at the off-diagonal components, you obtain a considerably large fraction in their value compared to the diagonal ones, but at largest scales, again, they go to 0. And finally, let me just say that you also obtain TB and EB angular correlation functions They are non-zero here. They are zero in the isotropic models, but not here. Though they are non-zero, they are small. As you see, this is a small fraction of the BB angular correlation function, 10 to the minus 5 versus 10 to the minus 3. But still, they are there. They are going to be difficult to be observed because they oscillate around 0. But still, this is a smoking gun of a possible anisotropic evolution of the early universe. And I think with this, I will just conclude. I will leave here the conclusions. Very rapid, very fast summarize that essentially we have extended the standard model by considering anisotropic inflationary models. We saw that it is necessary to go beyond GR in order to make any prediction in this model, because in GR you have the problem that at high curvatures you don't have a well-posed initial value problem for perturbations. Still, you can consider other interesting models, bouncing ones, and use Planck data to constrain the amount of anisotropies in these spacetimes, compute angular correlation functions, and you see that tensor perturbations, they show a stronger coupling with anisotropies that translate in a higher amplitude of BB angular correlation functions. And finally, we also get non-zero TB and EB correlation functions that are identically zero in the isotropic limit. Thank you so much for your attention, and I will take any question from you.
Thank you very much.
Okay, so thank you for the talk, Javier. Anybody, any question? I will ask one. Sorry?
Let me ask this one. Statistically speaking, you said a lot about the constraint. Is there some features or some discrepancies, some tensions in the data that your model is better at explaining, that your calculation is better at explaining that the usual isotropic cosmology?
Yeah, so Planck has been able to constrain quadrupolar anomalies in the CMB. They don't get confirmation that there is actually a quadrupolar anomaly. I think they got an anomaly, quadrupolar anomaly between 2 and 3 sigmas. So this is a small evidence of quadrupolar anomaly. But somehow this indicates that these kind of scenarios could be phenomenologically interesting, because not only they are compatible with present observations, but they actually provide additional observables that perhaps could be interesting if one is eventually able to observe the BB angular correlation function. We have not observed this guy here yet. We only have constraints. But if eventually it is possible to see this guy, who knows? Maybe one could think about looking at these kind of features in order to check whether the universe at very early times was really homogeneous and isotropic, or if there were some departures of this state.
Okay. Let me ask you another question regarding anisotropy. So you were showing a potential for a scalar field at some point, yeah? You were plotting it. So what is the Lagrangian? What is the matter Lagrangian of this system? Is it just a scalar field?
It's just a scalar field, minimally coupled. The only thing is that it is minimally coupled to loop quantum cosmology.
Okay, because the energy momentum tensor of a scalar field is compatible with a FRW solution, which is homogeneous and isotropic. So this coupling is what introduced the anisotropy.
No. What is introducing the anisotropy is just the background geometry, namely the Ricci scalar in the Lagrangian.
Yeah, but what I'm saying is that the energy momentum tensor of a scalar field, if it is just a minimally coupled scalar field, I understand that in your case it's not, but I'm just making this general statement, that would be necessarily homogeneous and isotropic.
Oh, yes. You are completely right. Yes.
Yeah. So somehow the energy momentum tensor of your system is not homogeneous and isotropic in order to be compatible with an inhomogeneous background metric, correct?
No, my metric is not inhomogeneous. It's homogeneous, but it is anisotropic.
Correct. Anisotropic. Correct.
Yeah. So in principle, the stress energy tensor of the scalar field is still homogeneous and isotropic because it's just a scalar field.
Okay.
Right. The only thing is that it's the space-time geometry which has the anisotropy. You have like an additional geometrical degrees of freedom. They have nothing to do with the matter content.
Okay, but because of the Einstein equation, the symmetry of the physics, let's say the symmetry of the left hand side and right hand side of the Einstein equation, to be compatible. So that was the thing I was trying to clarify. But
oh yeah, I see your point. Yeah, this is. Let me think 1 second. Yes, I have an answer. The thing is that you can actually take this model, and I don't have the questions here, but you can actually, if you consider the mean scale factor, and you look to the equations, to the Einstein equations with respect to this point of view, you will get the usual ones, the Freeman-Robertson-Walker equations in a FRW model. The only thing is that in the Freeman equation, you will get an extra contribution that is coming from this guy here, the sigma square over 2k. And you have an additional set of equations that completely decouple from the matter sector that account for how the remaining components of the shear evolve. So this guy here is completely determined by the scale factor because it completely decouples from the matter content.
But okay, but then in that case, it's a perturbative. It cannot be part of the background because
no, it is part because it enters in as a contribution in the Friedman equation.
Yeah. But what I'm saying is that the Friedman equation normally does not have it. But maybe we can clarify it later. Maybe there is something I'm missing. Thank you.
Okay, no problem.
Okay, thank you very much. The time for discussion is up. And now we move on to the last speaker of the session. And we are going to discuss the questions of power, or the power spectrum, one spectrum to rule them all, and Alexander Gallego.
Okay, hello everyone. Maybe, can you see the screen?
Yes.
Okay, perfect. Okay, can you see the mouse?
Yes, we can.
Okay. First of all, I would like to say hello to everyone and thank to the conveners for this parallel session. Let me just have everything ready. Can you see me?
You mean your face?
On? Yes.
No, I can't, but I don't know if other people can.
Okay.
You want to be seen or not?
Yeah, maybe. It's just, there's no need actually.
Okay, as you wish.
But now I lost. Okay, now I know how to do it. Okay, so let me begin again. So again, thanks everyone, especially since this is the last talk. So you might be real tired, but thank you a lot. Okay, so this work was done in collaboration with Professor Antonio Romano from the Universidad de Antioquia. It is based this work in 2019. I'm right now, actually, I'm here at Universidad de Valparaíso in Chile. And let me begin by telling you the main results of this talk. And I will try to relate it to relate the talk with the formation of primordial black holes and most of the talks that have been given here. So one of the first results is that we find that there is an infinite family of dual slow parameter histories. And by dual, I mean that there are models which can produce the same spectrum of scalar perturbations. And we show that this degeneracy is related to the freedom in the choice of the initial energy scale of inflation, meaning the Hubble parameter, the initial Hubble parameter. And we also show that the degeneracy can be broken at the bispectrum level, except larger scales in the squeeze limit configuration, which is related to the Maldacena squeeze limit consistency condition. And what this means is that regarding some results and the violation of some consistency conditions, we show that not all of them can actually apply. So there could be a violation of these conditions, consistency conditions. But as I said before, the Maldacena squeeze limit consistency conditions is still valid, as I will try to show you. And finally, I will try to talk just a little bit about the primordial black holes. Especially, I will try to say that the dual models, they could actually predict the same mass fraction of primordial black holes formation when we consider a Gaussian PDF. Okay, for the formation of the primordial black holes. I will try to argue a little bit about this. Okay, in order to show this, I will divide the talk in 4 parts. Then first I will give a brief review of primordial cooperative perturbations. Then I will talk about the origin of dual models. And then I will show the results. And finally, I will conclude. Okay, so the motivation for this is that in this work, we found that there was a degeneracy related to the discontinuity of the derivatives of the inflaton potential. Okay, so we started to think, how could we find or relate a general result to the degeneracy in the power spectrum of the curvature perturbations? So we started to think about this, and we finally found that there was a relation between this degeneracy. It was related to the energy of the inflaton of the inflation. See? The initial energy of inflation. Another motivation to do this work was that we know that there are several inflationary models which can produce the same primordial spectrum, and we would like to distinguish between them. And we know that some way to do is by studying the higher order correlation functions, like the bispectrum or the trispectrum. And another motivation, and final motivation, which has been of real interest in the last years, is that maybe the detection of the induced gravitational waves, which are produced during the formation of primordial black holes, they could also discriminate between these dual models. So I will try to argue this a little bit about this. Okay, so as for the dual model, let's start with a brief review of primordial cooperative perturbations. But I have to say that the results here are very general. They could apply to different models, even to multi-field inflation. And they can be applied especially to any model for which the anisotropy and entropy effects are negligible. So in general, there is no need of specifying an inflaton potential, okay? But just keep in mind that there should be a negligible anisotropy and entropy effects. Okay, we will use the usual slow roll parameters as given in equation 1 and 2, where h is the Hubble parameter, a is the scale factor, and from now on, dots will indicate derivatives with respect to time. Okay, so as some of you have shown before, the second order action for the scalar perturbations is given as equation 3 under this under the assumption of negligible entropy perturbations. And as you can see, it depends on the scale factor and the slow roll parameters. And here M is the reduced Planck mass, and R is the curvature perturbation and co-moving slices, which is the quantity that we are going to be interested in. So the mode equation means that the equation for curvature perturbations in Fourier space is given by equation 4, where Z is defined as an equation 5, K is the co-moving wave number, and now prime is the node derivative with respect to time. Okay, so these are the usual equations. These are the initial conditions that we will take for the mole function, for the mole equation. So it's given by equation 6 and 7, and in the bunch there is vacuum. And as usual, we will take the 2-point correlation function in order to obtain the primordial spectrum of curvature perturbations, which is given in equation 10. So we solve the mole equation, we obtain the curvature perturbations, and then we can calculate the primordial power spectrum as in equation 10. And similarly for the 3-point correlation function, from them we can obtain the bispectrum, which is given for these integrals. And then we will try to see the degeneracy, the breaking of the degeneracy between these two quantities, between the power spectrum and the bispectrum. Okay, for the bispectrum, we will study the degeneracy given by equation 12, the usual FNL function. And okay, so that is the formalism so far, which is for most of you very well known. But now let's go back to the mole equation. I'll write it here again in equation 13. And as you can see, the evolution of the curvature perturbations depend on Z prime over Z, which are given in terms of the background quantities. Okay, so it means that for any background quantities, or for the Z prime over Z, the same for any models, they will give me the same evolution of the movement curvature perturbations. So as long as this term in red is the same, all moving curvature perturbations will be the same. So that is the degeneracy. That is the most general way to find a degeneracy between different models. So this is something that we found really interesting. And in fact, even if you have Z prime over Z, the same for different models, you will get that the background quantities and even the high order correlation functions are different. So there is a breaking of the degeneracy at the background and the high order correlation functions. So this Z function, which is given in equation 14, as you can see, can be specified just in terms of the scale factor, the derivatives, the first and second derivative of the scale factor. And as you can see in equation 15, we just have reorganized the equation 14. And if we set the same Z for different models using different initial conditions for the scale factor, we will get the same power spectrum. What I mean is that if we fix Z such in order that you will have a different evolution on the left-hand side when you choose different initial conditions, but as long as you have the same Z, you will have the same power spectrum. So this is in general what we study in this paper. And we found that it is related to the initial energy of inflation, to the initial Hubble parameter. Okay, so this is the freedom that we have as in equation 16. So as long as we set an initial energy to the inflation, we can change it, because here in equation 15 we can fix the scale factor, the derivative of the scale factor, which is related to the Hubble parameter. So as long as we fix that, we can have this freedom, and this freedom will give us the degeneracy in the power spectrum. So that's what we did. In order to show you that, we will use some analytic solution. This is just to have an example in which we can have a form for the scale factor in which we can obtain analytic solutions for the background and for the perturbation quantities. This is the only reason why we choose equation 17. So in that case, we will have analytic solutions for background and some perturbation quantities. So if we choose the scale factor as a reference, this scale factor as the reference one, meaning that from equation 17, we will calculate the Z ref as in equation 15. As long as we have that, as given in equation 18, as long as we have that, we will have the same spectrum. So remember that we have a freedom here in choosing the initial conditions for the scale factor. And we did this for a featureless scale factor as given in equation 17. But it can also be done for a future scale factor as equation 19, where you can see that we have used a feature, the scale factor, in which will be there will be a peak for the scale factor, which will give you an enhancement in the power spectrum. So we will have some features in the predicted power spectrum, but even in this case, as I will show you later, even in this case, there will be a degeneracy in the power spectrum. Okay, this kind of feature was studied before in these papers. So again, what we'll use is to obtain this scale factor as the reference. Let's say, but it's actually a dual model. We will insert it in equation 20, and then that will give me an evolution for the power spectrum, but I will use another, which is the dual. I will use a dual evolution when I change the initial condition for the scale factor. So they both will have the same Z, so they will have, I will obtain the same power spectrum. So by summarizing, what I mean is this: we first solve equation 21 for A using a different initial condition, and from that, now that I have A giving me the same Z, I can obtain all the other background and perturbation quantities. I can obtain the evolution of the slow roll parameters. I can obtain the evolution of the convergent cover to perturbations. And just to show you some plots, I will use this freedom in the initial energy condition, which is given by delta H, given by an initial value for the Hubble parameter that I will choose, given by the derivative of the scale factor, the time derivative of the scale factor, and by this H reference given by one of these scale factors. Okay, so this is just a parameter. We will use this delta H equal to 0.98, but just to show you some results. And here in this plot, I show you that chosen a different scale factor, a different evolution of the scale factor, giving me the same Z, which is in blue, are the different evolution, the additional energy conditions for energy evolution for the equation 21, while in red is this Z ref calculated with these analytical expressions for the scale factor as in equation 19 or equation 18 and 17, sorry. So using that, I can have the same Z. And what is important here is that, okay, I have the same Z. Let's see how are the background quantities and how are the perturbation quantities. So this is what we obtained. We found that on the left, there are the featureless scale factor, and on the right is the future scale factor. And as you can see, even though when they have the same Z, as shown here, the background evolution is different. For instance, for the epsilon slower parameter, we can see that they are different. On the right, you can see there is a little bump. Here is just given by the future and the scale factor. And for the second slower parameter, the eta parameter, you can see that again they are different. And in fact, there is well, the eta parameter is an increasing function of the number of e-folds. And here on the right, you can again see the feature here given by the feature in the scale factor. This is interesting because you can actually move, or you can actually see what is the effect of the feature at the end of inflation. For instance, in trying to understand or trying to predict the formation of black holes, primordial black holes at the end of inflation. And here's the power spectrum calculated on the left, again, for the featureless case, on the right for the featured case. And as you can see, even when they have the different evolution of the background contrast, they give me the same power spectrum. So you can see the blue and red, they coincide. Even when there are some features, as in the on the right, even in this case, the power spectrum is degenerate. They produce the different models produce the same power spectrum. And then we started to think about how about the high order correlation functions. And as you can see in this plot, we studied the squeeze limit of this configuration. And on the right-hand side, you can see that there are some, there's an agreement between the dual models, which corresponds to the Maldaceno's consistency condition. But as you can see, for smaller scales, the models actually predict a different FNL function. So even in the featureless and featured cases. And another interesting feature here is that, as you can see, even when for the red lines, there are no features, that is just an evolution, a featureless evolution. Even in this case, the dual models predict a signal for the bispectrum, which is really interesting, because it shouldn't be flat; it should be zero, as in the blue line case. Okay, now for the equilateral limits, we calculated the similar results. We can see that actually the degeneracy is broken at this bispectrum level. Even in the on the right, when there are some features, the degeneracy, there are some points where they can coincide, but actually they are different. Okay, so these are the main results, especially that the power spectrum is degenerate, but the bispectrum is there is a breaking of this degeneracy. So the conclusions are that we can show that we actually show that there is a general degeneracy in the power spectrum. We found that is given by the choosing of the energy condition during inflation, or given by this Z function. And this degeneracy is broken at the bispectrum level, at the high order correlation functions. And this is interesting because from CMB data, we could actually distinguish between different models predicting the same power spectrum. This breaking of the degeneracy, it might be related to the violation of some consistency relations in which they relate the power spectrum and the bispectrum. And most of them do not survive because there is no one-to-one correspondence between the spectrum and the bispectrum. The only one that could actually survive is as the Maldacena consistency condition. And then finally, I will say that the dual models could actually produce the same mass fraction of primordial black holes, a formation, when we use a Gaussian probability distribution function. What I mean is that if we use this Gaussian probability distribution function, this probability distribution function is given in terms of the primordial spectrum. And since there is no way, or since there is a degeneracy in the primordial power spectrum, we could produce the same mass fraction of primordial black holes. But this is just a work in progress. Okay, thank you.
Thank you very much.
Okay, thank you, Alexander, for your talk. Do we have time for quick questions? Okay, so please ask questions if you have some question for Alexander.
If I could ask a question, I'd like to know this thing. Normally, I would write that the power spectrum of curvature perturbation is proportional to h over epsilon. So, and this h over epsilon times a constant numerical factor is evaluated at the time of the Hubble radius crossing of a given node. So, is the degeneracy that you're talking about related to the fact that for for a given PR, I can have different H's for different epsilons and vice versa?
That is something that actually this work we try to understand, because as you can see, there is there is no degeneracy in the epsilon, and there are some plots in which we calculated the relation between the H and the epsilon, and they were different. But what you're saying is that is correct. It's something that we should have to look for, because yes, when we fix the energy of inflation, let's say by the detection of primordial gravitational waves, we will fix the value of epsilon, and that will fix the value of the initial energy of inflation. So yes, it's related to that. Yes, it's related to the freedom that we have in choosing the epsilon parameter, or equivalently the energy.
Can I express my opinion about this?
Yes, sure.
So I would say that
formula,
that formula is just an approximation. So that formula you're mentioning, h squared over epsilon, is an approximation, but in practice, that's the reason why this kind of effect was missed before, I would say. Because if you, I don't know if we have tried that, but I think if you try to plot h squared over epsilon for the models, for the dual models that we consider, it turns out that it doesn't give you a good approximation. So one way of looking at this is there is an exact formula for z double prime over z, okay, which is exact in slow roll. So one way of looking at it is to think that you are looking at this expression and you're looking at models which have a certain specific combination of slow roll parameters such that z double prime over z is the same. And if z double prime is the same, z is the same, then I think it's a stronger condition than the one we consider, but still it is because we just impose z prime over z, which is the same. But it's enough, I would say, to understand what happens. So you have to go behind. Basically, you have to take into account all the slow roll parameter to see this the origin of this.
Okay, I have to go beyond the slow roll.
Yeah.
Okay.
And not necessarily. I would say beyond the epsilon. Like it's a matter of order of slow. You have to go beyond first order in slow roll. Yeah.
Yes.
Okay, thank you.
Yeah.
Because I wouldn't say, I think the models we consider, they don't violate slow roll. They don't, yeah? I don't know. Show, can you plot eta? No, they don't. So, well, it could be that higher order slow roll parameters, they're violating the slow roll hierarchy. It could be. Because I can see here there are some sharp variation in eta. So I would say probably the third order slow roll parameter may violate the slow roll hierarchy. So it's something that has to be studied numerically, basically. But it's difficult to see using slow roll expansion. So I ask you one question. So regarding what you were saying about the PDF, okay, so you were saying that if you approximate the PDF of black holes using a Gaussian distribution, that depends just on the 2-point correlation function. Okay, so then if you think about it in the opposite way, then could you say that by comparing the PBH prediction of different models, then you could be able to distinguish, basically resolve the degeneracy? Because if you show that higher order correlation function, they do break the degeneracy. So that also means that the PBH, if you are different abundance of PBH would be able to break this degeneracy as well. Yeah.
Yeah, they could. In fact, but that is taking into account the non-Gaussian contribution for the PDF.
Yeah, because that's what I'm saying.
Yeah, yes, because as we can see, there is a breaking of degeneracy at the bispectrum level.
Yeah.
So only if you consider the non-Gaussian contributions to the PDF, you can actually you might distinguish between.
Yeah, but basically PBH could be another way to distinguish between these dual models.
Yes.
I mean, assuming the non-Gaussian contribution to the abundance are important. Yeah.
Yes, but that is expected actually, because if in order to have some formation of black hole, primordial black holes, you might need the enhancement of the coverture perturbations in some formalism, some others. So if you are using these features of this enhancement of the coverture perturbation, there will be a non-Gaussian contribution to the PDF. So you might have to take it into account.
Okay. Now we are a little bit past our allotted time, so this is now time to wrap up our session. Thank you very much, Alexander. I would like to thank to all the speakers of this session. And with this, I'm going to close it. And yeah, I hope that you're going to remember this session fondly.
Okay, I would just like to add one more question, one more observation, that all the talks about CMB were very welcome. This was not a PBH session, so it was in fact CM4, if I'm not wrong. So it was just the general topic. It turns out to be a lot of talks in black holes, but all the talks also which were not necessarily related to black holes were very interesting. Thank you.
Thank you very much. And normally we would clap, but I mean, this is the most that I can do.
Okay. Okay.
Okay, thanks to everyone. Thank you.
Thank you.
Thanks, everyone. Goodbye.
Bye.
Thank you. Goodbye.
Bye-bye.
Bye. Thank you.
Thank you. Goodbye.
Bye-bye.
Okay, I'm the host, so I'm just going to finish this meeting, and I understand that this will bring the recording to the end, and the organizers will take care of the recording.
Okay. Thanks. Bye.
Thanks. Bye-bye.